Hi all, welcome to day 4 of the Improving Scientific Software Conference. Today we're going to get a tutorial led by a whole group of folks. The speaker is listed as David Bernholdt from Oak Ridge. Just some kind of boilerplate stuff. Obviously, make sure everyone should follow the UCAR Code of Conduct and be respectful to all of those in attendance. The other detail is that if you have any questions during this tutorial, make sure to post them into Zoom chat. We will not have Slido for this tutorial. I think that's all I have to say. So David, feel free to take over. Thank you.
Thanks very much, Jesse. Good morning, everyone. Welcome to the Better Scientific Software tutorial. I just want to mention at the outset that we have a set of slides for this tutorial that you may want to download. Some of this stuff we'll be presenting will move fairly quickly, and you might want to have these to refer to later. And we just updated the slides this morning, so if you have downloaded them from the ISS Google Drive site before now, you might want to update that. Another place that you can get them, which I'll talk about in a moment, is the tutorial website, and one of my colleagues can put the link for that in the chat, make it a little more accessible. So we have a group of people from various locations, institutions, who are going to talk to you today about our experiences in trying to produce better scientific software. I'm David Bernholdt from Oak Ridge National Laboratory. We have Patricia Grubel from Los Alamos, Rinku Gupta from Argonne, and David Rogers from Oak Ridge. And this afternoon, we'll also be joined by Anshu Dubey and Greg Watson. And we are all members of the Ideas Productivity Project. Ideas is a part of the Exascale Computing Project that focuses on increasing developer productivity and software sustainability and scientific reproducibility in this context. And we do a lot of outreach activities as well as working with ECP teams. And this is an example of one of our activities. If you're interested in learning more about the project, you can see how we work and things like that in this report that's in the bottom left corner. And we have, as part of another part of our project, we have a site called Better Scientific Software, just the same name as the tutorial. This is a community-based site to provide resources for scientific software improvement. We welcome you to visit and make use of the resources there. We also welcome you and encourage you to contribute things that we may not have already on the site that you find useful. And if you want to follow us in the future, we have a mailing list that we announce many of our activities. We do a monthly webinar series. We do panels about remote work, which occur quarterly at present. And we have a lot of activities at some of the major scientific meetings, like ISC coming up in a couple of months, supercomputing, many SciAm meetings, things like that. And also the bssw.io site has a monthly digest where we just update you on what's new on the site. So these are some easy, low volume ways to keep up with things that we're doing. Within our group and within our tutorial, we're very concerned about inclusivity, and we try to pay attention to this in our own tutorial. If you find examples where you think we can be more inclusive, please let us know. And I'll also just mention at the bottom of this slide, we have links to a couple of resources if you are interested in learning more about inclusivity in software development. Now let me mention again the tutorial website. So bssw-tutorial.github.io. That's kind of the one canonical place that you can find all of our tutorial information. Each of our tutorial events has its own page there, so you can go to the main page, find the page for this this tutorial and get all the information that we're providing you. You'll see the full agenda. There is a link to the slides. There's information about the hands-on exercises. And also there's a section called resources from the presentations, where we've actually taken all the links that appear in these slides and put them right there in the page so that you can access them a little more easily. And this will be there for you to go back to. Once the videos are available from this event, we'll link to those as well. Also, we have some hands-on activities which are associated with some of the talks that we'll be presenting. This gives you an opportunity to try out some of the concepts that we're talking about, and we can help you work through those if you want. We'll have some time this afternoon in which you can work on these activities, or if you want to just work on them on your own, we're happy to engage with you at any time. So we do have a session this afternoon where we'll have, it's kind of a choose your own adventure. We will have a few talks because the presentation part of the agenda, I made a mistake and it carried on longer than it should have. But then we'll have an opportunity for you to do hands-on activities, and we can help with that. We'll have some opportunity for more Q&A about the presentations, or opportunity for general discussion about your own software development experiences. You might want to share, get ideas from us, get ideas from your colleagues, and we found this to be a really useful kind of thing to do in our presentations. I want to go back for a second and explain slide 2. I skipped over it here, but in all of our presentations, you'll see this slide which has the license for the content, which is a Creative Commons license. It has the citation that we request if you want to refer to this, and it also has the acknowledgements. And one of the big acknowledgements that we want to tout is our sponsor, the Exascale Computing Project, that's made this work possible. And this is maybe the first example of a good practice. This isn't software per se, but it's always good to have a license to provide citations to your work that you prefer people to use, and also to acknowledge your sponsors. So this is maybe the first best practice that we can present to you. We really want to interact with you as part of this tutorial and afterwards. So as Jesse mentioned, please use the Zoom chat to ask us questions at any time. We'll be available during the break if you want to have more interaction. And of course, as I said this afternoon, we have some free time, unstructured time this afternoon that we can do those things as well. If you want to work on the hands-on activities today or at any other time, we'll be glad to provide feedback on your issues and pull requests that you might want to file as part of those activities. And we have a mailing list that you can reach us at any time. So with that, I'm ready to move into the first presentation. Unfortunately, Rinku Gupta, who is slated to give this presentation, is having some network problems this morning, so I'm going to cover it for her. I hope people won't be too disappointed with that. Also, one other thing that I wanted to ask folks, if you want to put a few words in chat to introduce yourself, so that we know a little bit more about you and our presenters can introduce themselves too in this way, that would be a nice start on the interaction that we hope to have to learn a little bit more about you. So now we want to give kind of a very quick overview of some of the motivations for the material in this tutorial, and talk about how we approach this challenge. One of the fundamental messages that we want to convey today is that science through computing is at best as credible as the software behind it. This is a sort of a message that you'll see repeated throughout our presentations. We've seen a lot of success in recent years in computational science, kind of across the board, getting better understanding of complex physics phenomena. If that motivates doing even more, and we are able to build more and more capable hardware, and we have better math to go with it. And we get into this virtuous cycle that's shown in the upper right, where we keep building ourselves up as a community, computational science community, but it also sets expectations higher and higher. And what we find these days is that software is getting so large and complex that really you need quite a variety of expertise to really do a proper job. And the only way in many cases is to approach that through a separation of concerns. You can't expect one person to know everything about a large, complex software project. And so what we need to do fundamentally is to have a bunch of people who can work on the same software project in different roles. And to do that effectively, you need some kind of software engineering process. And if you say, well, no, my team's really small, we get along well, we don't need a process. Actually, even if you don't document it or set it out explicitly, you still have a process. It may have accumulated over time, just the way you do things, but you've got some process going on. And so it's worth thinking about that and thinking about it a little bit more systematically, and where it might be causing you pain and how you might be able to improve. And then we get into this further situation, especially in recent years, we've seen a huge rise in the heterogeneity of the computing platform. So we've got GPU accelerators, we've got a lot more interest in FPGAs, other kinds of computers, quantum, neuromorphic, other AI processors. And the requirements here are unfolding and they're not known a priori. So the only real way to deal with these kind of challenges is to look ahead and invest in a flexible design and a robust, well-defined software engineering process so that you can focus your attention on the new challenges that are coming up, and have, be comfortable in dealing with software engineering issues and things like that. And there are lots of challenges today. We have technical challenges as well as sociological challenges, right? On the technical side, we're dealing with these large codes, and just about anything in the package can be considered a research issue at any given moment. Requirements may change throughout the life cycle as our understanding of the problems and a desire to deal with new things comes in. Verification, we're mostly dealing with floating point code representing physical phenomena in one way or another, and the verification of those types of algorithms can be particularly challenging. And basically, the real world that we're trying to model is messy, and so as a result, our software also ends up messy. And then there's this issue of the architectural diversity that I referred to. And on the sociological side, there's competing priorities and incentives. Our sponsors, unfortunately, often care more about the publications or the scientific output than the quality of the software per se. We have to balance the development that we do and the maintenance that we do with the new research that we produce. We have limited resources to do this with, and we need to interact with a bunch of different people from different disciplines. And that can be a challenge sometimes. So there's a lot of concerns here. And we've all heard about a variety of challenges where failure to pay adequate attention to details of the software has led to unfortunate consequences. In some cases, on the left is an example where people have actually died because of inadequate attention to testing and software engineering principles. On the right is an example where we lost a very expensive space probe because of inadequate testing at a software interface. These are just two of the many examples out there. I'm sure you can come up with others. But there are also more subtle impacts on scientific productivity that you might need to think about. And an example here is a while back from the Flash astrophysics team. They were offered an opportunity to access one of the fastest machines in the world at that time, a Blue Gene L, and get a dedicated run. They had very short notice. They were given less than a month to prepare for a run that would run a week and a half. So they did some quick and dirty development of a particle tracking capability in the code. And unfortunately, after the run, they realized that there was an error in the tracking code due to duplicated tags due to round off. Excuse me, floating point round off. And so they actually had to spend 6 months to develop post-processing tools to deal with this bug. And so this is an example where even though the Flash project had a good software process in place, the situation that they were placed in meant that they couldn't apply the normal rigor that they did to their software development, and they ended up having to pay for it in the end. So this is just another example, more subtle than some of the ones on the previous slide, but still very important. Fundamentally, what it comes down to is this concept of technical debt. Like monetary debt, the more you accumulate, the harder it is to pay off, and it has increased all around the software that you're working with, and it fundamentally reduces your software productivity, your ability to develop software at the pace and at the quality levels that you would like, and it impacts your scientific productivity. Another aspect for many of us is that we're working on large supercomputers that are provided by various funding sponsors. These things cost a lot of money, and it takes a lot of effort to get an allocation on them. Even if you don't have to actually pay for that allocation, you want to make sure you're being a good steward of these resources. You want to show the sponsors that you're doing a proper job with the resources they've given you, and for your own sake, you probably want to try to get as much science out of the allocation that you're given as possible, because these allocations are precious. So there's a lot of reasons to think about good software. Our experience is that good scientific process requires good software practices. That feeds back. Good software practices increase software sustainability, increases scientific productivity, and so you get better results in the long run by paying attention to your software. What are good software practices? Well, there's no fixed or universally agreed to set of best practices for scientific software. The specifics will depend on your software, how it's used, who's on the team, and things like that. But there are a few examples that we can look at to get some ideas. And so I'm not going to have time to go into these in detail, but there's a paper from Greg Wilson and others that's called Best Practices for Scientific Computing. And some of the high-level messages they advocate there: write programs for people, not computers. Let the computers do the work. Focus on incremental rather than large changes. Don't repeat yourself, and plan for mistakes. Also, optimize the software only after it works correctly. They talk about design, documenting the design and purpose, not the mechanics. And they talk about collaboration around the software. There's a follow-up paper to this called Good Enough Practices in Scientific Computing, because their experience was that the best practices could sometimes be hard to follow. So they wanted to step back a little bit and say, well, what's good enough? And they advised some practices in terms of data management, in terms of, so this is the process of doing science with the software, in terms of the software itself, in terms of how to write manuscripts, in terms of how to collaborate with your colleagues, how to organize a project, keep track of changes, etc. And then another example is that the Linux Foundation has something called the Core Infrastructure Initiative, which has a best practices badging program. This is not something like the previous two. They were focused on scientific software. This is not specifically intended for scientific software, but it's a useful set of principles to look at as well. They define 3 levels of capabilities, basically, and it's a combination of must and should criteria. And so the kind of things that they look at are, having a project website, having a license, basic documentation, other aspects of that, having change control, bug reporting, quality control. In a larger Linux, in a larger context, security is often a consideration, and this is something that is also coming up more and more in scientific computing, especially as we get to more and more into workflows and distributed computing and things like that. They advocate for the use of static analysis and dynamic code analysis and things like that. But an important thing here, especially with these last set of ideas from the Linux Foundation, is that software engineering advice taken from the larger world often needs adaptation for scientific software. So the experiences reported in the wild may apply to other contexts, but they don't necessarily consider the special nature of scientific software. That doesn't mean that we should ignore all the other software engineering experience that's out there. There's a lot of useful concepts and approaches and tools. And many of those we can just pick up, but we need to be thoughtful about it. And we also need to recognize that in some cases, it might be useful to adapt these ideas, and some of them just might not work. So we encourage, first and foremost, a thoughtful approach to what your project needs. Be ready to adapt processes so that they work better for you and your situation and your team. Don't be afraid to experiment with these things. And there was actually a tutorial yesterday by some of our colleagues from the Ideas Project on the PSIP process, which I'll have a slide on in a second to recap. But then, so we've all this talk about software engineering. So the question comes up, how much time and effort should I spend on software engineering? And our advice there is that your project should include just enough software engineering so that you can meet your short-term and longer-term scientific goals effectively. More than that is icing on the cake, but if you have research commitments, you're trying to satisfy sponsors with research goals and things like that, this is really what you should be thinking about, helping ensure that you can succeed in those scientific goals. So this PSIP process that we talk about is a process of continual, incremental software process improvement. So the strategy here is to identify your team's pain points in the software development process. There's some tools that can help you do that. Set a goal for something to improve. You should target processes and behaviors, not just tasks that need to be done to make the software better. Pick something that's modest in size that you can address in a few months and will give you a noticeable benefit if it succeeds. Agree on a plan and how you're going to identify that you've made progress and how to define done. And those you can write up as something called a progress tracking card. And then you work to your plan, you track your progress with the progress tracking card. And when you achieve what you consider to be done, you celebrate. And then you can pick a new pain point to address. And the whole goal of this process is to incrementally bend the curve. So instead of making straight line progress, try some new things, and hopefully they'll help you lower the cost of your software development processes in the future. So there's a link to resources about the PSIP process. And as I mentioned before, we have this site, bssw.io, that provides general resources and things to think about for improving your software development processes. So in today's tutorial, we're going to talk about a variety of topics. We don't have time to cover everything that we might like to. So we're going to talk about agile methodologies. We're going to talk about a little bit about Git workflows as a way of collaborating around software. We're going to talk about testing software in a couple of different modules, some scientific software design. That's the morning. Then in the afternoon, we're going to come back and talk a little bit about refactoring of software and the refactoring process, have kind of a whirlwind discussion of reproducibility, and then we'll have the time we talked about to do the hands-on and discussion and things like that, which will be very free form. All right, and that is the end of the overview, and now we will turn to Pat Grubel from Los Alamos National Lab, who's going to talk about agile methodologies. And while Pat is bringing up her slides, also feel free to put any questions in chat if you have any at this point.
So do you see my screen?
We do.
Okay. There we go. Is that the right screen then?
It is.
Okay, so I'm Pat Grubel from Los Alamos National Laboratory, and I'm going to talk about Agile. And again, this is our citation slide. So this talk is about Agile, and just a second, with an emphasis on small teams. And hang on a second, I'm sorry. First, I'll go over some of the things that affect small teams to emphasize the importance of applying Agile methodologies to help manage some of the challenges associated with small teams. I'll explain Agile and Agile workflows. We'll get familiar with some of the common terminology and approaches, and then I'll talk about some of the tools that are available to help you starting these methodologies and give you more productivity for your small team. Small scientific software teams are usually composed of 1 or 2 senior faculty or PIs and several junior members who may be students or postdocs or other junior staff. And stability of the project usually depends on the senior staff, while the junior staff tend to have limited time on the project. They may be graduating or transitioning to other roles in their career. Senior staff have the vision for the project and know the overall goals, but they don't usually do the coding. And the junior staff usually does the coding, but are entrenched in the details. But again, they may transition in and out of the project frequently. Although this talk emphasizes the small team, large teams are many times composed of smaller teams. So the methods can be applied keeping in mind that extra interactions with the larger team or with other sub-teams. There are many challenges that small teams have. They may have informal structure and they less clearly defined processes. Processes that work for large teams in places such as industry and enterprise systems may not work well for small teams. In small teams, there's often a flux of membership, especially among the junior members who are most familiar with the details. Many of the junior members have other items to focus on, such as graduation requirements or publishing. Small team membership may be in constant flux. There need to be processes for newcomers to ramp up quickly in several areas, such as the details of the concepts and the tools that are used for that project. Also, upon leaving, there is a need to make sure the work they have done is retained and that their knowledge is handed on to other team members. The team member lifecycle demonstrates the importance of procedures and checklists for onboarding, policies for continuing work, and checklists and procedures for departing members. The first phase for any new member is initiation and setup. Then there is a ramp-up phase. It can be quite extensive depending on the team member's experience, as well as the processes required and how well those processes are defined for the new member. The next phases are active work, involving planning and actual work. Even in these areas, it helps to have clearly defined policies and to ensure that they are followed and updated as needed. If the team member is a student, postdoc, or has some type of term appointment, the time period is usually known, and that makes it easier to plan for their departure. So it's important to have processes in place to ensure the transfer, that their contributions are preserved and used by the project. And once a replacement is appointed, or anytime a new member joins the team, this cycle is repeated. There may be a variety of checklists for a project. Here's an example, a snippet from an onboarding checklist for developers joining the Trilinos project. And if you want to look at it in more detail, you can look at the site that's on this slide. Checklists are essentially to-do lists and can be improved by adding items or updating them as they are discovered either missing or some part of the information has changed. And you can do that as you are onboarding someone and you discover this. There can be a variety of checklists think about what kind of checklists your team needs. Maybe you need a checklist for code review or some part of your development process, or even team behavior, documentation. Think about the checklists that would help you and start developing them. The development tools from the SDK project is a collection of libraries and tools that are from independent projects, but they're specifically targeted to address performance at scale. So these policies are used across the community to ensure consistency. We show the link here because you could look at these policies and see what would help in keeping your project consistent during development. So checklists and policies can be effective in mitigating the challenges that teams have. Now I'm going to talk about what Agile is. So what is Agile and why does it work for small research teams in the scientific environments? In these types of environments, your work pattern may be disrupted by results. Your focus may need to change to presenting new results or publishing or even making changes to the model. Heavyweight techniques may not be flexible enough for these changes, but in a small team, you can adopt processes that are beneficial for your team and focus on areas that you need to. You may need to focus on productivity or sustainability of the software. Heavyweight approaches do not usually fit the scientific domain well. For a small team, using Agile allows the team to choose the processes that are beneficial and can adapt them to their needs. So the main idea is to choose what helps your team. Now we will talk about Agile and what it is not. It is not a traditional software development cycle. It doesn't have phases that a traditional model has. Sometimes Agile is described as being Scrum. Scrum is widely used in the enterprise communities to help teams work together. Scrum is Agile, but Agile is not only Scrum, much like a square is a rectangle, but not all rectangles are squares. So, and then Scrum in scientific teams hasn't really been explored that much. But we do use Kanbans, and they can be seen as a tool to aid Agile methodologies. I'll talk more about that in a little bit. More information about what Agile is can be found in the Manifesto for Agile at agilemanifesto.org. I'll go through some of the principles, but don't have the time to cover them all. There are 4 critical components, however, which are shown above the red box. Now, if you look at what's in the red box, you notice that it says that although the principles on the left are usually more important than the ones on the right. So we emphasize the ones on the left over the ones on the right. So let's go over these principles. Individuals and interactions over processes and tools. We look at working software over comprehensive documentation. Now that doesn't mean that documentation isn't important. It is important, but working software does take emphasis over it. So don't use it as an excuse not to do documentation or have good documentation. But the most important thing is that your software is working. Also, there's customer collaboration over contract negotiation and responding to change over following a plan. In other words, you can be flexible. Well, so look over the manifesto and read the 12 principles for deeper understanding. We'll go through a few of them now. The 12 principles are listed in the next 2 slides. I don't have time to go into all of them on detail, but you should read them as you can. Here are some important items that are highlighted in red. So let's go through the first 2. Our highest priority is to satisfy the customer through early and continuous delivery of valuable software. Agile actually focuses on this principle because a lot of heavyweight lifecycle software processes use a long time for developing and testing before delivering the software. And then when the cycle is at that point, they deliver software that may have where the requirements or even the target environments have changed. Then the developers have to fit the changes in a very quick time to satisfy the needs of the stakeholders. So Agile tries to circumvent this by having early and regular delivery, perhaps including changes that come up during the development process. The second principle is to welcome changing requirements even late in development. Now, this doesn't mean that a stakeholder can change or add new requirements every day or hold on to requirements and pile them up late in the development. But there should be a way to be flexible and be able to offer development for important changing requirements. Here are the remaining principles with some important ideas highlighted again, such as having processes that promote sustainable development and maintaining a constant pace for stakeholders and developers. Reflection on becoming more effective. Read through the 12 principles to get a deeper understanding, especially if that interests you. The principles are not meant to be hard and fast rules, but guides. Pick a practice or a few practices to try and use the ones that work for your team. Add them to your processes. It may be easier to get started with basic principles of Kanban and add the practices as you can and build them incrementally. So here is a basic Kanban board. I like to think of it as an organized to-do list with status, maybe divided or labeled by sub-projects. Basically, every project has tasks that needs to be done and are in various stages, such as shown in the columns here. Items that are backlogged, those that are ready to develop, those that are actually in progress of development, and then those that are completed. You may have other columns, such as maybe you have reviewed, in review, or blocked items. Or if you're a student, maybe you have a column called waiting on advisor. You can be as creative as you want. Design the Kanban however works well for you and your team. There are basic principles that you should follow for Kanban. An important principle is to limit the number of tasks that are currently being worked on. This limits the cost of context switching for your team members. Each team needs to determine the number of tasks that can be active or in progress. A good rule is to have 2 times the number of team members minus 1. Kanban is good at exposing bottlenecks. If you have a column like waiting for review or block that is full, you can easily see the bottleneck is not getting timely feedback from your collaborators, or maybe for a student from your advisor. Once a bottleneck is identified, the team can work on fixing the processes that affect it. Kanban avoids a deadline approach, more common in Scrum. Deadlines are dealt with in other ways. Kanban is a nice way to manage tasks and view progress of the project to ensure steady progress and improve productivity. Kanban can also be used to organize your personal life and/or your personal tasks for work projects. You can dive deeply into the subject for personal Kanban in this book, or you can go to the article on our Better Scientific Software website, bssw.io, which David mentioned earlier. The article has links to a few quick references for personal Kanban and points to some of the tools that I'll talk about in the next slide. It also has other helpful articles for productivity for both teams and individuals. I use Kanban to manage my work, where I have to manage work on several different projects. I can see the progress of my tasks and ease the cost of the unavoidable context switch. You can also use personal Kanbans for managing your personal life, and you can share your Kanban with team members or family members. Let's look at Kanban tools. So here we show some basic Kanban tools. You can even start out with a blackboard or a whiteboard with Post-it notes. like in this example. And then you can transfer it to one of the cloud-based ones if you want to. There's many. There's Trello, Jira, GitHub, issues, and the project boards associated with GitHub or GitLab. And there are many more. Trello is a free software. It's rather useful because you can update it from a browser or your smartphone or an iPad. So you could update it or view it from anywhere. And you can have different boards for different contexts. It's also very effective for people who are split on multiple projects, like I was telling you I do. So the big question is, how many tasks should I have on my board? I started with just a few tasks for each of my projects and have increased them over time. I think I have around 5 columns and 40 or so tasks with labels for each of my projects. If you add too many tasks to the board, it can become like a packed highway. The traffic doesn't flow up well. So you should start simple and add as you go. Make sure you update it and consult the board often. You may be very enthusiastic at the beginning, and then sometimes you lose interest. That happens to me. It's happened even to my teams. When it happens, it's okay. You can come back to it and start up again. It does help to make a habit of consulting the board regularly. In my personal project Kanban, I have a today column, and I move things in and out so I can kind of keep track of what I'm going to do that day. And then I consult my other columns regularly. The board helps you keep in mind how well your team is doing, what team members are working on, and what the bottlenecks are. It also helps with reflection and retrospection and improves productivity. If you have a Kanban board, you will have a clear picture of your time. It helps you to focus on your work, and if a new task comes up, you can determine if you have the bandwidth to work on it or what you might need to put on the back burner to give you that time. This can set up a good discussion with your team members or your advisor or supervisor, and it can also help you to negotiate what time should be spent on the new task or whether that task can even be added. If you were to come up with your own new task that you're really excited and enthusiastic about, you can look at your Kanban and help plan how you will fit it in. And also then you can maybe use that tool to help you with negotiation with either your supervisor or advisor or other team members. So let's talk about Kanban, how we can build on Kanban. The focus should be on solving issues. One helpful way is to have regular short stand-up meetings where team members can report on progress. You can have planning meetings, retrospective meetings on what has gone well or what hasn't gone so well. Now we will look at epic, story, and task. The concept of epic, story, and task has worked well for both research teams and enterprise teams. The idea of epic story task is that you start with the high level requirements, and they are broken down into lower levels when you need to. This is done in that manner because a lot of time might otherwise be spent in defining the low level requirements, and those become outdated when the task actually begins, and that wastes time. So the idea is to spend that type of effort closer to the start date of the task. So epics are very high level objectives, and you refine epics, you will have stories. And then epics usually have several stories, and those stories can be broken down into several tasks in order to complete a story. Once you have completed all the tasks in a story, those are checked off. And once all the stories in an epic are done, your epic is complete. One way to define epics and stories is to have user stories. User stories are something to help you, your customer, and team understand the requirements and processes. It helps the development team and stakeholders to understand the overall process. As an example of a story, you might say, as a team lead, I want to learn Kanban in order to manage my team better. The user story would be important for adding productivity of the team. The stories are used to improve communication and elicit information about the requirements from the stakeholders, and also to help the team to fulfill goals of the project. And here's some examples that go along with our heat example in our hands-on for developers. So you might look at these types of stories and think about what you would need to add for your epic and stories. So epic. So epic is derived from the user stories. It can help you with refactoring code, enhance modularity, those types of things. Here is a sample of Kanban board from the Collegeville organization. Explore this example. It's a real world example. See how they use Kanban and see if some of their ideas can help you to manage your project. It might give you some ideas for your Kanban board if you want to start one up. So I just wanted to mention GitHub or GitLab, wherever you might have a repository for software development. Since many projects use GitHub for development, it's easy to use the project boards on GitHub as a Kanban. They're basic Kanban boards, and they give you the ability to map the submitted issues in your repository to columns on the project board. It doesn't have to all the features that some of the other tools have, but it's quite easy to use. And like I said, it's available on the same site where you keep your projects. In fact, I was introduced to Kanban through GitHub project boards. And as I mentioned, I actually organized my personal work on a GitHub project board. And several of my projects have GitHub project boards that are used for Kanban. So it lacks some of the more important advanced features, like there aren't dependencies between issues, but you can reference an issue from another issue. And it doesn't have advanced notification schemes or custom fields. You can create custom labels. As I said, I create labels for each of my projects in my personal work board. And then I can actually filter the display so I can look at just one project at a time if I want to. So there are ways to use it. And it's, like I said, again, it's good because sometimes you can use it on the same area where you do your software development. Another thing you can look at on the is the A-Team tools, where we have a collection of resources for applying some lightweight agile practices. We invite you to explore that site. And another reference that we have is the books here. These have all been highly recommended resources for helping with your productivity and your agile workflows. Next, I'm going to talk about Git workflows. And again, here's our slide. So version control is an important part of software development. Some of you may be familiar with Git, so I don't plan to cover the basics commands, although we are willing to help anyone during discussions in the hands-on area in the afternoon. What we are going to cover are the mechanisms that workflows use so that you can determine what will be useful. I was looking at the chat. I don't know if there's something important there. I just skipped into this section, but feel free to unmute David and let me know. I will show you some different types of Git workflow models and some Git workflows used successfully by several scientific software teams. Many items are distributed and many teams are distributed and team members have a separation of concerns. So they may work on various parts of the code. They want to collaborate efficiently so that the code will be sustainable and produce correct results. Git workflows help many scientific software teams attain these goals. The basic the basic Git workflow is a I'm sorry, it's not really Git. The basic workflow is a centralized workflow. And this is a type of workflow that many of the older types of version control systems use. Some of you may have worked with Subversion or other workflows where there's a centralized remote repo. By default, when you start a Git repo, it will have a main branch. And if you use this model, it can work for some personal development or maybe a very small team with good communication. Since all commits to the remote repo go in the one location, it can become very difficult to collaborate since developers may commit at different frequencies. And it becomes hard to ensure interfaces work well. Testing also can be very difficult. So I'm going to go over other models, and this model and those will be in the Atlassian Bitbucket site. So if you want to get deeper into those, into these types of workflows, you can look there for more details. Next, we'll look at the mechanisms that help us create workflows that are more amenable to collaboration. Those mechanisms are branches, pull requests, and forks. These mechanisms allow collaborators to build workflows and policies that aid collaboration. Developers can easily work on different parts of the code in parallel. Reviews and testing can be performed and before merging into the main branch, and contributors can contribute from outside the team. Branches are the basic mechanism used to build a variety of Git workflow models. They create independent lines of development. Branches enable developers to work on a feature or an issue separate from main. Those changes can be tested and refined before merging into main. A developer can work in a branch and make commits to the remote repo without changing the main branch. So the main branch is protected and changes are stored and can be shared through the remote repository. Once a feature has been completed and tested, it can be integrated through a merge commit. Workflow policies aid collaboration. Policies prevent unnecessary complexity and make collaboration more efficient. In the case illustrated, there are two branches with names that are not meaningful, and they start and end from different places. Imagine that the policies, if any exist, are not clearly documented, and there are many software developers doing these type of changes on the team. The result would be a repository that has many complex branches, and parallel development would be difficult. Some policies that might help prevent the problems that are depicted in this diagram include giving your branch a descriptive or meaningful name. Name the branch for the feature you are implementing, or link it to an issue. You may set a policy for where branches start, such as all branches must begin from main and be merged into main or another principal branch. A special type of branch is a feature branch. In a feature branch, developers usually work on some sort of feature, and when it is finished, it will be merged into the main branch. And then the feature branch can be discarded. Developers can work on different features and fixes simultaneously. The example on the right shows two people, Alice and Bob, working on one repository. You can see that Alice has downloaded the main branch to her local machine and has created a feature branch for add solver A. She started from commit C of the main branch and has added 4 commits. Bob also downloaded a copy of the repo to his local machine and started a branch to work on issue 151. But he apparently downloaded earlier and started from commit B of the main branch, then added 3 commits. You can also see at this point in time, the remote repository had a main branch with commits A, B, and C. Their development causes a divergence from main and each other, but can be merged to collaboration since they are using separate branches. This diagram shows a feature branch diversion in Bob's local repository. You can see that Alice merges into the main branch in her local repo and that she has no issue. So she pushes to the remote repository and deletes the branch. At this point, her local repository has identical commits to the remote repository. Alice merged her commits and pushed to the the remote repository first. Bob then pulls main from the remote repository and gets Alice's changes in his main branch. But he tries to merge his changes into main. He gets a merge conflict. He will need to fix the conflicts, and this time may want to communicate with Alice for the best path forward. Bob has a feature race condition since he started from commit B. So Bob rebases issue 151 branch to the latest commit on main. He can push his branch to the remote repository, and Alice and Bob can review the branch, communicate, and work together to resolve the conflicts in the branch. The feature branch can then be tested, and when all is fixed, it can be merged into main. Feature branches are usually deleted after merging into the main branch, but many workflows have lifetime branches in addition to main. Lifetime branches are not ever deleted, or they may at least exist for a very long time. These branches are in all the copies of the repository and serve different purposes. For instance, there may be a development branch where changes are made frequently and may not be stable. And there may be production and pre-production branches that are considered stable and are released. There may be other lifelong branches, such as ones for testing. The Git workflow of a particular repository is comprised of the lifetime branches and policies for their use. In this example, the policy is that feature branches start from the main branch and are committed to the development branch. They are most likely reviewed and tested before commit to development, and may undergo even stricter tests or need to comply with project policies before being merged into main from development. You can see in this case that there are several commits into development from the add solver A branch. Then apparently it was finalized and committed into main. The next mechanism for collaboration in Git workflows is the pull request, or if you're using GitLab, it is called a merge request. Once changes are completed in a feature branch, the developer can create a pull request. This alerts the development team that changes are ready to be merged into the main branch. A pull request should be reviewed and tested before the merge. This allows discussion about the pull request and possible iterations of more commits on the branch during the review. A reviewer or set of reviewers can be requested for the pull request. Maybe you want to select an expert in a particular area to review the feature you just developed. Or you might make sure the person who submitted an issue that you are fixing reviews the change and tests it. As with branches, setting policies for pull requests are part of the overall Git workflow. Policies can include things like what tests must pass and how many approvals, or who, the makeup of whoever is going to approve it are required before merging. The last mechanism I'm going to talk about are forks. Forks are very powerful mechanisms for collaboration, especially in open source software. A fork is a complete copy of all the branches of a repository into a different account. Anyone who has read access to the repository can create a fork of it. For instance, if some users of a code that are not on the main development team want to add some special feature to the code for their own use, they can fork the repository and work on the feature in a branch in their work. They can even give write access to their collaborators that don't have write access to the main, the upstream repository. And if they complete the feature and feel that it would be useful to the wider community, they can suggest the addition of the feature through a pull request to the original, or what is called the upstream repository. The maintainers of the upstream repository can review their features and decide whether or not to merge it into their main repository. So forks are valuable for contributions from outside sources, but also keep the control of the original repository within the team that maintains it. Since maintainers keep control of the original repository, they can prevent the huge number of branches that might occur if there was another model. There are some caveats. If you fork a public repository, that repository is also public. And when making changes in a fork, you should always make your changes in branches other than main. And but issues from the upstream repository and pull requests will not be in your fork. And forks are very valuable to the open source community since they allow contributions from outside the software team. Those were the main Git mechanisms that are used for Git workflows. Now I'm going to briefly talk about peer code review. This is an important part of the software development process. Peer code review is when developers convene to check code for implementations, that coding guidelines are followed, and to find errors. Code reviews can accelerate the software development process since there are many benefits. We outline some of the benefits here. Discussions about the change can lead to more iterations on the code to improve or correct it. During a code review, reviewers may not have worked on the part of the code under review, and that gives them a better understanding of a part that they may have not looked at before. And it also can give them a better understanding of the overall project and its requirements. The impact of the change on other parts of the code can be assessed. Will it break other parts? What are the implications of changes to interfaces of other parts? These are the things that can be considered. Also, there is a benefit of learning new techniques that can be applied to the own reviewer's development process. Here's a link to a short blog by Hugo Sousa on how to code review a PR. It's a quick read and may help you get started, including these types of reviews for your project. I'm sorry, I just see that I'm running over, so I'll go through this a little bit quicker. So far, I've talked about the mechanisms of Git workflows. Now I'm going to review some of the models. How much time do I have, David?
Well, we're actually into the break already. So
Oh my
yeah,
goodness.
I think you need to wind up pretty quickly.
Okay, so we do have these models of different complexity. So I would suggest that you go through them. Through the slides, and if you have any questions during the discussion later, we can go through some of them. It's nice to look at these projects, what they've actually done, and you can base some of yours on that. I thought I had 45 minutes total.
Well, whatever.
Okay, anyway.
I can't do the math that fast.
Yeah.
So sorry about that, folks. Yes, to quickly recap the point of the slides that Pat's
Let me go through this slide real quick,
yeah,
David.
okay, here you go.
The main thing is that you need to adopt what's good for your team. And if you would go through some of these models, and if you want to during this afternoon session, we can do that. Start simple and add complexity where it's needed. That's the biggest thing. Sorry about going over.
Yeah, and let me just add there that the different examples that Pat had to skip over were really the primary questions there are about what is stable and what is changing and how often it's changing and things like that. And you can make policy decisions that will help you have things that have certain amounts of stability that you can sort of promise to users of that branch or whatever, to give them certain characteristics to facilitate your work together.
And I can't stop sharing, so somebody else can stop me, I think. Okay.
All right, thanks, Pat. Apologies for going over. We are now into the break. We'll resume at 20 after the hour. We will be available for questions during the break if anybody wants. Of course, we'll also have more time this afternoon to get into questions and discussion if people want to come back for that. So I think during the break, maybe put the questions in chat and we'll see what we can do to respond. Thank you. Go ahead, Rinku.
You're muted.
My apologies, I was muted. So good morning, everyone. My name is Rinku Gupta from Argonne National Lab. And in this module, I am going to be talking about software testing and how it is used in the development process in scientific computing. So this is our license slide out here. And this presentation has a lot of material, and I'm going to go through it fairly quickly. The slides will be available for you to glance over if you want to revisit it. The presentation module is divided into two parts. In the first part, we'll talk about testing concepts and terminology. We will discuss some of the challenges of testing in scientific computing. And then I'll quickly show you an example of how to set up a Python project with testing. And then we'll discuss how to use the CMake framework for C and C++ projects. In the second part of the presentation, I will quickly walk through a testing method for larger and more complex projects based on something called as a heat equation. And then we'll take on from there. Now, who is the audience for this presentation? This presentation hopefully will provide some useful information to all of you. The first group of people are people who are new to software testing and are looking for advice on how to get started. And the second group is those who are working with legacy projects, but need to use or integrate a testing system with their existing code. And the third group maybe are people who are using testing, but are looking at ways to improve their testing practices on existing projects. Now, there's a lot of theory and associated terminology about testing, and sometimes it can be confusing. So for this tutorial, we'll focus on what is called as dynamic testing, which is testing by executing the code itself. And tests are often separated into two types: functional testing and non-functional testing. Now, functional testing is testing all components systematically against a set of requirements or specifications. For example, unit testing, integration testing, acceptance testing, and so on. Non-functional testing, on the other hand, is related to how the program operates or behaves. For example, it could be performance testing or stability testing or security testing. There are many different types of tests and testing strategies, and I'll just mention a few common ones. And the first three on the slide are somewhat of a hierarchy. So at the bottom, we have unit testing, which is really to check if a single routine or a single function is operating correctly. The next level is integration testing, which is to check whether a group of components or functions are operating correctly. Then you have system testing, which is to check if the program operates correctly as a whole and meets specific requirements. And then in addition to this, there are other strategies like regression testing, which is to check if the changes that you may have introduced in the code, they've not caused problem to the expected behavior of the code. And there's acceptance testing, which is kind of similar to system testing, but it checks the program as a whole and ensures that the software meets the requirements of the customer. So what is verification validation? How does it relate to testing? Now, the terminology for verification validation is a little different in scientific computing versus software engineering. So verification in software engineering means that you are checking that the software conforms to the design and the requirements. And this is, of course, beyond testing to ensure that the documented requirements are all met. Testing in software engineering plays an important role in the verification process to check and make sure that each aspect of the code is working as it should be. In scientific computing, on the other hand, verification aims to ensure that the code is a correct representation of our underlying mathematical model. And many times verification involves comparing the model solution to a reference solution, checking for convergence, and so on and so forth. So that's verification. Validation in software engineering is used to check and determine if the code meets the customer needs. So it can be system level or acceptance testing may need to be performed. But in scientific computing, validation is much more complex because it may involve determining the accuracy of the model, comparing the output with experimental results, and it may sometimes also involve using a computational model to make predictions that can later on be verified. Testing within this slide out here shows testing within the software development lifecycle. Now, scientific software development is a complex project, complex process, and there are many parties involved with expertise in different subject areas. So from the slide, you can see in the physical world, you may have domain experts who understand the overall problem. They may have a set of models in mind. They may propose equations that are required to solve the problem. Also, the domain scientists would have considered validation checks arising from different, physical mathematical properties of their models. So you have the domain experts, and then you see applied mathematicians out here who take all these equations and work with numerical solvers and work with discretizers. And they have a good understanding of functional spaces, convergence criteria. They can address issues related to model fidelity, and so on. And then you have computer software engineer, computer scientists out here that map the problem into programming models. They contribute things like extensible interoperable frameworks with a focus on productivity, sustainability. So you can see from the slide that testing in the software development lifecycle happens in different parts, and many parties are involved out here. So now the question is that when should a test be written? When you actually write the test, in reality, often testing is left until the very last possible minute. And that's not good, because tests sometimes are written as an afterthought. They're added to later on test the code or test for bugs. But rather than adding the test as an afterthought, it has been shown that writing the test before you write the code can lead to great outcomes. And this is known as test-driven development, also called as TDD. Now, one of the advantages of test-driven development is that now developers can think about what it means for a problem to be correct. They're not trying to just see what their function is trying to do, but they understand the overall goal of the problem. Another advantage is that because the tests themselves are comprehensive and they have to be written in advance before writing the code, they end up becoming the specification for the eventual program. But there are challenges to this, because you have to take care in writing tests. You have to think carefully about what you're testing, because really there's no code at that point, right? So people are not used to doing it, and therefore it could be challenging. You also need to make sure that you run the test very frequently. And this is where things like continuous integration comes in. We will touch upon it later on. And one important thing is that when you're using TDD, you should be using it across the whole team. You don't want some people writing tests before the code, some people writing tests after the code. It has to be adopted by the entire development team. So, what does this TDD look like? What does test-driven development look like? How does it work? So the first step is to actually write a test that describes a particular aspect of the program that you are trying to implement. It can, as I said, it could be a bit challenging for people to figure out the functionality of the software before you actually code it, but it is an important step. Now, once you've written that, you run the test. Now, of course, the tests have just been written. They're going to fail because that feature does not exist yet, right? So the next step is to write enough code to make the test pass. And so this cycle of writing enough code, running the test, writing enough code, running the test, this continues until you get to a point where all the tests pass. Now, in that iterative process, you would have used shortcuts. You could have introduced some temporary code that may not be best from maybe sustainability point of view. So the next thing to do once the code has been written and the test passes is to refactor the code. And you remove all this extra stuff that you've added, and you make sure that the code conforms to any requirement that the project has. And at this point, you've reached a stage where you've implemented that specific piece of functionality that you set out to do. And then you just continue to the next piece of functionality, and you do the same process over and over again till we have completed the entire specification of the program. Now, research software has some pretty unique challenges compared to traditional software. So let's deviate a bit and talk about what are the challenges in scientific computing research software. So first, let's talk about exploratory software, right? The primary thing in research software is essentially we're exploring new areas, and we don't really know what the expected outcome can be. So even after all the expected behavior of the program, after we've checked it, we still have to rely on domain experts to help validate the model and to iterate on the design. So it's a bit different compared to software engineering. In software engineering, you have a pretty clear idea of what your outcome is going to be, and you can just go and implement it. So there are some challenges in testing in scientific computing because of the exploratory nature. Also, a lot of scientific computing codes are legacy codes, and that can be difficult because legacy codes have a lot of expected behavior. They may not have any tests written for them, or the test may be lost, or the developers may have quit. And adding new tests can be a problem because we may not know much about the code, how it interacts, what part of the codes are working, and so on. So in the test-driven development approach, the very accepted way is to move forward with legacy codes. You don't try and implement tests for everything, but you begin implementing tests for whatever new functionality that you add. Lastly, I will talk a bit about release codes or production codes. The third group, this is the third group of codes, and typically these codes are made available to the broader community. And what is required in these circumstances is a thorough code review, which verifies each part of the code and addresses all the intended uses. And we need to ensure that whatever fixes we are making in such codes go through. So the testing approach could be quite different compared to our traditional testing methods. So now I want to jump in and discuss how to set up a Python project with testing. In this first example, I'm going to show you how to set up a new project that you can immediately start to develop, implement, and test. Writing code in Python is very, very easy. You just start with a text file. And first of all, in order to do this, we are going to have to install a couple of Python packages if you already don't have them installed. We are going to use something called as PyScaffold to create a Python package. And this will include the necessary files for the packaging and for the building of code. What is PyScaffold? It is, you can think of it as it's essentially a project generator, and it's used for bootstrapping Python code, Python packages, high quality Python packages. So what we do is to install PyScaffold, you just type the command pip install PyScaffold, and that should install it. Pip is the package installer for Python. So we install that. We also do pip install Tox. Tox is a package that manages the test within the project, and we go ahead and install that. And that's all we need. We just need to install these two packages. Then PyScaffold provides a command called putup, and this is all available on the screenshot on the slide. I hope you can see it. So PyScaffold provides this command called putup, which essentially creates a new project. So we say putup auto QCT, and that essentially creates a project with a scaffolding, and it incorporates tests within the skeleton module, and then you can modify and create your own program. So then we just simply run, we can simply run the tox command. And when you run the tox command, you will see this output that you see on the big black screen out here. And you see that it actually runs this test called PyTest on your behalf. And it will run, the PyTest will have a bunch of tests that is run. So it will run some kind of a Fibonacci test. It will run a main test. And you can see that this test have passed to some degree. One bonus thing that PyScaffold provides it provides code coverage. So it also runs a code coverage command. It will show you how much code coverage your tests are achieving. And now you can, once you have this in place, you can essentially customize this whole thing by adding, your own files. And this has good documentation of options with Sphinx. It has, it's a nifty thing to use. So let's talk now a bit about the codes that are based on C, C++, Fortran. And for such codes, the CMake build system is very popular. And CMake itself provides a pretty easy way to build test with something called as a C test framework that is available in it by default. So out here, you can see the CMake list or text file. And you essentially have to add a few lines or macros to this text file. To make it easier to use. Now, I've put a mention of this, this thing called BLT, which is basically a project from Lawrence Livermore National Lab that essentially provides a set of make files that can be used for designing and building, that can be used for building Google tests or, Fruit, that is for Fortran. And it provides code coverage, it provides code continuous integration, it's documented. So it's, again, a good thing to use. And in this example, out here, I'm trying to show how to easily create a CMake infrastructure. So the first screenshot out here shows CMake list file. We add a bunch of macros out there, and at the very end, we put a line which says include BLT setup BLT.CMake, and this will incorporate the BLT functionality into your project. The next few steps essentially consist of cloning the BLT repo, building our project by running CMake and make, and eventually you can see that you are running the test command, which will run all the tests, and then you see that the tests have all passed. So now going further, if you want to explore C, C++, Fortran, there are a variety of different tools for running and reporting on tests. For example, C- is a reporting and monitoring tool. PF Unit is a Fortran unit test framework. There's Flash Test that's coming from an ECP project. There are code coverage tools, there are static tools, and you have tools, similar tools for Python as well. Now, so even if you're trying to do test-driven development, where you write the test first, it's useful to know how much code is actually being tested, and that's where code coverage tools come in. Code coverage tools essentially allow you to visualize the lines of code that are being tested. And there are different types of code coverage tools. gcov, that is mentioned out here, is a standard utility that comes with the GNU compiler. There are different coverage tools there are different code coverage tools for different languages. There's something called lcov, which is a graphical front end for gcov. And it's fairly simple to use something like gcov. You need to use a particular option when you're compiling the code. And then you can run the code and you can use the gcov tool that will take the generated output and annotate the source code with the coverage information. I think we have that screenshot in this slide. Right, so out here on this slide, you can see that the source code is annotated. And so for every line out here, it will tell you how many times that particular line has been executed. If in front of the line, if you see hash symbols or pound symbol, it means that the line was not executed at all. So you can basically see what is executed, what is not. I like this quite a bit. This slide shows more tools, graphical tools out here, and they are like online tools that will help you visualize coverage. Okay, so we barely have any time, but for this last part of the module, I want to quickly walk through on how to use test-driven development for large complex code. We talk about the heat equation, and again, the slides are available to you to look at it in great detail later on. So the hello world example out here is essentially an implementation of the heat equation. On the slide, you can see that there are a lot of source code files that are provided that already implement the heat equation framework on how the code actually runs, and there are swappable kernels that implement different algorithms that are provided as well. So FTCS is one such kernel that has been provided, and our goal is to add a new kernel called Upwind 15 to use the test TDD process. So now the first few steps are easy. We download the code, we run the CMake command, we run the make command, and then we run the actual code by using the FTCS kernel, and then we see that things are working. And again, as I said, our goal is to add a new kernel called Upwind 15. So we want to add this new kernel. So we first need, because we are following the TDD approach, we first need to add the tests, and we need to decide what are we testing. Perhaps we are testing the convergence of the algorithm, or we are testing if the output is in a steady state, or we are looking at multiple precision. So we need to decide what we are testing. And in this slide and the next slide, we actually go ahead and create the test. So if you see, we are creating the test, we are enabling testing. So we are adding a test which checks the existing FTCS kernel. And then we are adding the test which checks the Upwind kernel, Upwind 15 kernel. And then we run the test. And of course, the FTCS kernel test will pass because it's existing. Upwind 15 will fail because that kernel doesn't exist yet, right? We have just written the test for it. So now the next step is to add the new kernel to make the test succeed. And so this slide shows that, that kernel was written somewhere by someone, and we are adding it to the source. And you can see that this kernel has been added to the source. We rerun the tests. And when we rerun the test, we see that the FTCS kernel passes and the Upwind 15 kernel passes as well. And with that, we've completed the first iteration of our test-driven development cycle. And then, of course, you can go ahead and improve on it. This slide has like some more ideas that you can try out to have different strategies. So I went through this portion fairly quickly, but as I said, the slides are available and are in great and are present in great detail. So take a look at it. Coming to the summary, a productive software team is always checking their work in some way using some type of testing. And it's a good idea to mirror the logical structure of your code into your tests because it helps understand how the tests relate to code. There are many different types of challenges associated with different kinds of projects. So you need to find something that fits your project. And the last thing is, don't get distracted by the tons of technologies out there. Just focus on something and pick it up and get started with it. And with that, I end my talk. There are a couple of resources out here that you can use if you're interested in terms of enriching yourself. And I am going to stop with that.
Right, thanks, Rinku. So I'm going to give Rinku a chance to breathe, and
Yes.
we're going to talk about design of scientific software a little bit before we get back into a little more about testing. So, we've had this experience over the last few decades that I talked about in the overview, where we've gotten into a virtuous cycle. Oops, I should turn on my camera. Gotten into a virtuous cycle, and we're doing better science, better computational science, which also generates the desire for even more improvement. And we've combined this with a situation where we're now starting to see a big increase in the platform complexity in recent years. So we went through 20 plus years where a fairly simple, by today's terms, distributed memory model for your computer and your software worked pretty effectively. But now we have all these heterogeneous processors and things like that that we have to deal with. So things have gotten a lot more complex. And of course, once again, any component in the software system may be the object of research. The software is continuously evolving. And in a scientific setting, pretty much anytime you do major production runs with the software, it's a different and unique case. So, you're stressing the code in different ways and things like that. And so we come up with a number of general principles that might help guide the design of scientific software in this kind of setting. So first of all, we're dealing these days with multidisciplinary teams. There are many different facets of knowledge, and it's not possible for everybody to know everything. So a design strategy to help deal with that is called separation of concerns. So encapsulate certain kinds of knowledge, certain kinds of functionality in different sections of the code so that you can shield developers from unnecessary interactions with things that they don't need to understand. If you encapsulate things and put good interfaces around them, then people should only have to deal with the interfaces, and as long as those are well documented and well tested, you should be in pretty good shape. Another consideration is really you want to think in terms of a couple different types of, paces of change in your code. One is the infrastructure that's relatively set. It doesn't need to change very much, and you can largely rely on it. And the other is the more rapidly changing scientific models, numerical methods, and things like that, which is where most of the development is happening. And the design strategy here is to explicitly separate your code so that you have these two segments so that you can easily distinguish what's long-lived code versus what is sort of quickly changing and maybe thrown away pretty quickly, or may evolve very quickly. And then the third consideration is that codes grow. We get new ideas, which turn into new features in the code. We really want code to be reused by others, and that often happens in ways that we don't anticipate. So you can try to design with extensibility in mind. You want to make it easy to add new capabilities. You want to make it easy to customize existing capabilities to facilitate these things. So a couple of general principles to think about, as I alluded to in the previous slide. Really separate your code into a couple distinct chunks, right? So in the top left, we have the parts of your code that are really most often the focus of your research. That's the models you're implementing and the numerical aspects of those models. And there will be client code associated with this that's mathematically complex, and that will need to change in response to what's going on on this first block, right? But then there are other aspects of the code that are more stable. So once you've settled on a mesh discretization technique, you probably don't need to worry about that too much. Your I/O, dealing with runtime parameters, things like that. Those aren't big, frequently changing things. You have other infrastructure. A lot of your data structures and data movement patterns and things like that can be pretty well defined, and you can implement them, and you don't need to worry about changing them very often. So you can separate your code this way, and you can apply all these concepts that are kind of repeat what we talked about before. Separate the concerns so that you have code that's well separated functionally. Encode, especially the more stable, the infrastructure components into a framework. Define the interfaces carefully and document them well. And also differentiate between what's protected or what's private in a code and what's exposed to the public. And expose to the public to other pieces of code, that is, as little as you can get away with, right? So keep as much inside the code so that people who just want to use the code don't have to worry about how the code is implemented. And lastly, you should think, today we hear a lot about different programming models, especially for accelerators and things like that. But your best strategy is to first do the design without consideration of the programming model, and then apply the programming model afterwards. Okay, if you design to a particular programming model, you're going to be whipped around. The next time you need to modify to a different programming model, you need to move to a different machine, you're going to have challenges, and they're going to be harder than if you tried to work with a design that was intended to be agnostic with respect to the programming model. It's not to say that the programming model won't have impacts, but we try to put them later on at a lower level in the development activity. So this slide shows kind of a straightforward graph or flowchart of how you can think about these things. On the left side, we have the infrastructure components of the system, and on the right side, we have the sort of science capabilities, the model, things like that are more rapidly changing. And so on the infrastructure side, you want to think in terms of requirements. What does the science that you're doing require out of a stable infrastructure? Design the API, implement it, test it, and maintain it. And then as you're going on with the science on the right side, you're modifying the model. You have to code to the API for the infrastructure. You do design work on the science side, you do development, you validate it, and you integrate, you test these things out, you integrate them into the code. You may find along the way that you need some changes in the infrastructure. If you do, then you may need to augment the infrastructure, at which point you come back around to modifying the API, you implement the changes, you test those carefully, and go back around. But you do it in a very thoughtful, controlled way so that you're not changing the infrastructure unnecessarily, while the capabilities, the science capabilities, are free to change more often. So let's think about this in terms of a simple example. We've already been referring to this little heat equation example. This is actually the physical problem we're trying to deal with. Suppose that you've got a pipe in a wall in your house. Outside, it's supposed to get really cold overnight. Inside, it's nice and cozy warm. When do you have to worry about the water pipe freezing? So this is the heat equation example we've been referring to. So how to think of this from a design specification? Well, or a design perspective. So first of all, what are the specifications? We have the heat equation, we have some initial conditions and some boundary conditions. And I didn't tell you this in the original question, but we want, because we're going to experiment with the numerics, we want to be able to easily apply some different integration methods to this problem. So what is the infrastructure here? Well, we can discretize things. We need to have a way of verifying things. There's some simple I/O that's needed. We have to, report some results. We have to apply the initial conditions. We have to get the runtime parameters, et cetera. What's the model? Well, we have this set of initial conditions. We have some boundary conditions we have to apply, and we have to integrate the equation through time. So what might your infrastructure API look like? Well, we might have something to process the arguments so that we can get all the, control the simulation. We have a way to initialize things. We need to be able to copy some data. We need to be able to write an array, and we need a way of setting the initial conditions. So these are generic infrastructure. In this case, it's a simple problem, so the infrastructure is pretty straightforward. Then the numerics, well, we want to be able to take a norm to measure how big our error is. We have several different solutions that we want to try out, a Crank-Nicholson method, an upwind method, this FTCS method, and then we have a way of computing the exact solution for comparison purposes. So we have two separate sets of APIs, and we can put those together. But that's a very simple problem. So now let's think about a more complex, more realistic problem. You have some multi-physics simulation that involves partial differential equations. How do these concepts map into that kind of situation? Well, basically, we do a couple of things in today's computing environment. We think about the domain that we're going to be doing this computation on. Right now, let's think of it as the square. And because we have a fundamentally distributed processor system, we need to do a spatial decomposition to put pieces of that problem on different processors. And what that's going to give us is really a bunch of independent computational units on each processors that may need to exchange boundary condition information between the processors. This is a fairly straightforward view of domain decomposition that probably most of you are used to. And if we follow something like this, then the considerations on this side of things become, the parallelization and the scaling of that data exchange and how to implement that efficiently. And then the other perspective is what's happening within each of the blocks. That's the functional decomposition. So here you have the math that's going on in each of these little domains, and you can view this math as a collection of components. And for these, since they're localized, their operation is localized, your primary focus areas here are on the memory access patterns and optimizing the compute so that you're doing that efficiently. And these are things that you can farm out to different people. So from the math perspective, implementing the functional aspects of the calculation, you probably want to engage some domain experts and some applied mathematicians, but a lot of these optimization activities can be done by your software and performance engineering colleagues. And so now we have a way of looking at this that has some infrastructure that handles the domain decomposition and some of the math and implementing the model and things like that. You can take this into a particular example. This is from the Flash code, which is now called FlashX. They have an approach that has components that, you can see just a few examples of the, several dozen components that are available in the Flash environment. They have an API to deal with grids. They have an API for adaptive mesh refinement. Then they have one for hydrodynamics and different variations on that. And they basically have a configuration approach that they can just configure these things to plug together based on their interfaces and interact with each other. And so they've got a whole setup here that allows the creation of a wide variety of very capable high-performance multi-physics simulations just by thinking carefully about this design that gives them all the separation into different types of components with well-defined interfaces and some tools that they've developed to help put them together in the way that they want for one simulation or another. Okay, so this is all very good. This is mostly focused on the distributed memory model, which we know is really kind of back in history. It's still part of the machines that we field today, but something else has taken over a lot. But the takeaways so far are you need to differentiate between the slow and the fast changing components. You need to understand the requirements on your infrastructure and implement a careful separation of concerns. Think about portability and extensibility and maintainability, and don't design with a particular programming model in mind. And now you come to today, where we've got all these different heterogeneous programming environments and computers that we have to worry about. And so do these design principles change? The answer is not really. The details get more involved, but the fundamental principles still apply. And so we go back to this, this flow chart, and the areas that are highlighted in purple are the sort of the contact points where the changes are most likely to interact with each other, right? So you may have to accommodate things like GPU accelerators and things like that. You are going to have to change things, and you want to think about them in an isolated fashion, right? So that these contact points are where you're focusing the changes that need to happen. So based on experience, we've developed some principles that can guide design in this new heterogeneous type of environment. First of all, you should focus on hierarchical parallelism, several levels of parallelism. So decompose to the nodes, decompose within the nodes, design towards several thousand threads of computation. Expect a hierarchical memory space. That means you may need to think about the data moving between memory spaces, and that has a cost associated with it. And so you want to include in your design the capability to be careful about which memory space you're in and be thoughtful about the need to move between memory spaces, be able to reuse memory and things like that. And all throughout this, you really want to avoid vendor-specific options. That can be hard, especially with some of the less mature programming environments that are tend to start out as vendor-focused responses. But it's something to be thoughtful about, and if you're careful, you can do this. So the kind of design considerations that we talked about before are still active, but we need to sort of generalize a little bit. So we need to start thinking, in terms of the domain decomposition. You may need to introduce some designs to deal with the load distribution more carefully, and management of the runtime so that you can pick up tasks and run them. And then on the functional decomposition side, you may, for example, start invoking some code transformations or alternate versions of code to accommodate different types of processor capabilities on the node. But a lot of the considerations are still the same. So fundamentally, when you get into this new, more heterogeneous environment, some of the big things to think about are, the structure of the data that will be effective on these with the new memory hierarchies and the new processor types that you're trying to worry about, and how to map the algorithms that you're using onto these devices, worry about the data movement so that you're not doing excess data movement that can be more expensive than the actual computations. And so fundamentally, the performance that you end up with is based on how well you think through this and do the mapping from your algorithm to the hardware. Some of the underlying ideas, try to make the same code work on different devices. There's a variety of ways to do this, but fundamentally, if you can let the compiler do it, or you may have to provide specializations for the hardware. You may have heard of tools like Cocos and Raja and other what are called template metaprogramming abstraction layers that help provide some tools to do this more easily. There's a variety of ways you can do this with if-defs in the code and things like that as well. And then you need to assign the work to the node and think about the data movement that's happening within the different processors and the different memories within the node. And you want to think about the platforms that you're trying to support and design for the commonalities that you see across the machines, not the distinctive features. And so even when you're using these third-party tools like Cocos or Raja or other things, you need to understand sort of what they're doing and something about how they're accomplishing their work so that you can use them effectively. So it's not, you can't afford to treat these things as a complete black box. You do need to give them, have some understanding of what's going on. And so the final takeaways here. So you want to think about performance, portability, and longevity of your software. And the best way to do that is to be thoughtful about the design of your software. So you should build extensibility into the design of your software. You should focus on being independent of any specific programming model, with the idea that you may need to move around and implement the code in multiple programming models over its lifetime. And think about composability and flexibility as a means to achieve your design. So there are a bunch of resources that are associated with some of the things that I've talked about here, and be happy to answer any questions if you want to put those in the chat, and I'll hand back over to Rinku. If that will stop sharing, there we go. Rinku, we're not hearing you yet.
Yes, I hope you can see the slide.
Yep.
All right, so I'm going to get started with the second part of testing, that is testing complex software. The first testing module that you saw earlier was about introduction to testing, types of tests, and how do you design them. And this presentation is mostly going to focus on how do you design tests for complex software. This is a license slide. The first question is, how do you build your test suite, and what forms a good collection of tests that will exercise your software in the way you want it to be exercised? So there are two levels of tests that we recognize. One is continuous integration, and that has gained popularity in the last few years. And that basically ensures that tests run as soon as you commit a code, commit a piece of code to your repo, or if you have a pull request accepted into the Git repo, that's when the continuous integration test will run and verify that nothing has failed. And these CI, continuous integration tests, are designed for quick diagnosis of errors. Now, in a complex software, you cannot have a comprehensive coverage through continuous integration because it will take too long. And you don't have that many hours to spare after every commit. So in that case, a second level of testing, which is called as nightly tests or scheduled testing, becomes important. Here, because you can afford to spend more hours, you can afford to have more coverage. So when you are thinking about granularity of tests, when you're thinking about devising your tests, you have to think about how do you want to mix the granularity. And the rule of thumb is that we want the test to be simple, but we also want to ensure that they enable us to quickly pinpoint the source of errors. Now it's important to devise tests for isolated components. And I'm choosing to call tests for isolated components as unit tests out here. A unit test in software engineering means something else, so we're deviating from standard terminology. So the unit testing out here may not be a single routine. It may be a collection of functions, but it's basically an isolated component of your code. And if such a unit test fails, then you know that the fault lies in your isolated component. The next step, is once from unit testing is to interoperate these various components, which means that you will need tests at integration level, system level, and they can be pretty complex. In the scientific world, you also have a specific class of tests that you don't always hear about in software engineering, and that's called as restart tests. So the reason why you have this is that when you're running your code on large machines, your code will take a long time to run, and you submit your job to a batch queuing system and you're given a time slot. So your job might not complete in one time slot. And so you may need to resubmit again and again, and it may take multiple time slots. And every time you resubmit, you want your code to restart from at a point where it previously stopped. So that, you basically want this restart to be as transparent as possible so that the final result has no idea that the job completed in several batches. And so it's very important in scientific computing to have these kind of restart tests built into your test suite for comprehensive coverage. So a lot of resources, you can find a lot of resources on the link that's given here that's pointing to the Ideas Productivity website. And there are a lot of resources on testing out there. So why not always use the most stringent testing? And the answer is basically lies on what are the resources available for testing for you. So no team has infinite resources, and creating tests and designing tests, basically this is a tax on the team. So you have to figure out what is the right balance. When the tax is too high, then you're spending too much time testing and you don't have too much time for code development. But when the tax is too low, then you are spending too much time developing the code and not testing the code. So it's possible that defects might sneak up in the code. So you have to evaluate what your project needs are and what your objectives are when it comes to testing. For example, if you just have a one-off test, then you don't want that one-off test to be very complex. You just want to make sure that it verifies the job that it's supposed to do, and then you move on. So testing decisions have to depend on the life cycle stage of the code size, the team size, and the degree of heterogeneity, the lifetime of the code, the complexity of the code, and so on. Life cycle out here basically means that, let's say a code is new, and for example, if you have a numerical method code, then you have to ensure that your testing is not only testing for correctness, but it's also testing for stability and testing for accuracy. Or if you have a production code, then you want to make sure that you're looking into areas that have not been exercised before, because you don't know what user will hit what area during production. And if it is refactoring code, then you want to make sure that you're testing any part of the code that has been touched when you're trying to refactor portions of it. So you need to evaluate your project needs. One thing to keep in mind is when it comes to good testing practices is what I mentioned in my previous talk in terms of verifying code coverage. So this is code coverage. I again want to emphasize it's not only just covering the lines of code, but you also want to make sure that you're covering when components interact with each other. You're covering all those scenarios. Another point is that you should have a consistent policy on dealing with failed tests. And those might come from things like how are you tracking the code, what needs to be fixed, who's responsible for fixing it. Another good practice is to have someone from the team watching the test suite and making sure that the decisions about the errors to be fixed are made in a timely fashion. Now, when you are refactoring the code or adding new feature, you should have a regression suite available before you check in the code, because it may happen that a part of the code that you've not been working on may be indirectly impacted. So it's important to have regression testing. Another point is that's very beneficial is to have code review before releasing the test suite, because somebody looking at a code with fresh eyes may be able to find something that you may have missed. And this is an incredibly, cost-effective method, and a lot of teams use it. So now let's get into, I want to move into some examples about development of tests. So the first scenario is test development for a new code. In this scenario, the development of tests and diagnostics usually goes hand in hand with code development. And having good diagnostic tests is important. And it is important to compare against simpler analytical or semi-analytical solution. Because what may happen in a testing environment is that, for example, you may have machine precision drifts happening, and you will have to convince yourself that the final answer that you got is different because of the machine drift and not because of some error in your code. But another thing is that you should build granularity into testing. I've already said that. But this granularity that you build can be used for scaffolding your test and building more confidence into testing. What is scaffolding? Scaffolding is any code that we write that is not a part of the application, but it is written to provide support for the process of unit testing, integration testing. And as I said, you build scaffolding to build confidence in your testing. Another point is always inject errors to verify that your test is working. And it's not always easy to write good tests, but it is extremely important to do it. So after looking at the new code, now let's take a look at how to develop tests for a legacy code. As I mentioned in my previous talk, in many legacy codes, the tests may have been developed on software. Those tests might no longer be available. And so what happens is when a user is dealing with just one component of the code, they have to run like the whole model, and this could take hours, and this could waste people's time. So the idea is that the method that is used by researchers is to isolate a small area of the code that we want to test. So for example, if we want to test this area where I have my cursor, I isolate this area of the code. And this isolated area of the code may be coming from somewhere in the middle of the code. So in order to start from a point in the middle of the code, what we want to do is we want to dump a state snapshot of that code at this point. And when we run the test, we basically just read the state snapshot, and execution can then be done from that point. So we don't have to run the entire model. While running the test, we also need something called as a test driver. And this test driver will usually work only in this isolated state. So the test driver will focus on working with files that are present in this isolated state. So if there are dependencies that exist between files, we want to make sure that those dependencies are taken care of. And then we might just want to create like a custom file that the driver can invoke. And essentially the point is that you're isolating all the dependencies into this one particular test unit out here. And if you do this, then you have your granular test ready, and you can read in the save data, and you can run the test and verify, whatever you need to verify. And you have to remember that we have to inject errors to verify that the test is actually working. So this example that I gave out here is one way to develop a test for legacy codes, and there are many other ways as well. In this third example, we want to build scaffolding and structuring, structuring for the test in order to pinpoint bugs in different parts of the code. So in this scenario, you can have components that are exercised against simpler application. And then you can try to build scaffolding for verification to gain more confidence in your testing. So like to give you an example, in this picture, you see this gray circle, semicircles, and these are mocked up dependencies, which means that you can run this test without exercising any other component in the code. Whereas whatever is in blue color, these are real dependencies, and the test will not run, and therefore it will not give you much information. Now, if all these dependencies are verified, then this will effectively verify the code. So this can be a bit ambiguous. So let me go into a bit more detail to explain this idea of building scaffolding and structuring the test with the purpose of quickly pinpointing out to errors. So this, what you see out here is actually a snapshot of like the shock hydrodynamics code that uses something called as AMR, which is adaptive mesh refinement. So let's focus on just building the test. So the first test we build is called as a guard halo cell fill test. It's also called as a GC test. In this test, I'll just go into some technical details. Let's assume that there are a lot of processes in this application, in this test, and let's assume my process, it's also called as a rank in programming model terminology. So my rank has been given an overall domain or data to work with, and the goal is for my rank to update these cells in its domain. The halo cells or guard cells are what you see in blue. They are surrounding my domain. And these halo cells actually get data. They contain data that comes from other processes. So, the halo cell around rank 2 will get data that comes from rank 3 and so on. And so my job is to, and I need this surrounding data to update, my individual cells. So the simple test for this would require just two variables. One variable I would initialize just on the cells belonging to my process, my rank, and I won't put values in the halo cells. The second variable I will initialize both for halo cells and my cells. And then, like, going to some details, then I would do something called as a guard cell exchange on the first variable. And in this condition, if the value in halo cells of the first and the second variables are identical, then the test is successful. So this is just laying down the criteria for the test to be successful. And this is one example of a standalone test. We could also build another test, which is called as an EOS test. It's called as equation of state. And going again into details, in this EOS test, we will check for consistency between calculation of energy, calculation of pressure based on temperature, density, and so on. Both the guard cell and the EOS cell are gray colored, and which basically means that they are standalone tests. So after building this standalone test, let's come to the building of scaffolding. You need scaffolding because you cannot execute the shock hydrodynamics code independently. This hydro test out here that you see in blue color, this has this will need both the GC test and the EOS test to run. And so this hydro test, let's go into details again out here. This hydro test is based on a well-known problem in hydrodynamics called state of the test problem. So for now, just believe that it's doing it has the code for testing out hydrodynamics. The hydro test, as I said, has dependencies on the GC and the EOS test. But if the scaffolding is right, and if we conclude that the GC test and the EOS test are passing, and if the hydro test is failing, then we know that the fault lies in the hydro test code and not in other parts of the code. So although the testing environment exercises the hydro and the GC and the EOS test modules, all of them, but it does it effectively. It does it in such a way that eventually this test will become a way of isolating errors in the hydro test portion of the scenario. Now, if we were to, exercise the mesh in an adaptive mesh setting, where the resolution changes depending on what other things are going on in the mesh, then the structure of the code and the structure of the restructuring of the test will again become important. For AMR, that is adaptive mesh, we need to check for specific things like flux conservation, regriddling, and we structure our test accordingly. And we reason about the, in the test, we can reason about the correctness of flux correction or regriddling by running the same test again and again. And this slide out here shows different combinations that you can run in different ways, which will help us understand the source of errors. This slide out here shows code coverage, and essentially it's a matrix where you have like a different set of capabilities. So you have hydro capability, like you have some capabilities along the column, some capabilities along the rows, and what you're trying to do is you're trying to run the test, and then you try to fill in the matrix. And your test can follow a specific algorithm. Like you can say that I'll first run all my unit tests, then I'll run tests sensitive to small changes. Then I can run tests that are important for solvers. Then I can run tests that are the least complex tests. So essentially, it's important. We don't have to fill the entire matrix, but the point is that we want enough code coverage to ensure that the critical elements of our code are hit upon using whatever tests we have designed. So the takeaway basically is that we have to understand the cost and the context when it comes to testing. We need to understand the needs. We need to devise tests that enable quick pinpointing of errors. We need to understand testing at the various granularities and whether we want to go with what complexity test. And the overall goal is that we need to have a holistic validation strategy. So that was the end of my talk. And if there are questions, please put them in the chat window.
Right, thanks, Rinku. I think we're just about at time. We need to cede to the next presentation, but just so everybody knows, we will be back this afternoon and have more of an opportunity to interact with you. We look forward to it. We really appreciate your participation this morning and hope to have more.
Great, thank you, David. And I want to let's give thanks to Rinku and Pat for excellent presentations, and let's give them all a virtual round of applause. So thank you. Next, we're going to have a presentation by Joseph Schoonover, I hope I pronounced that right, on continuous benchmarking applied to, I guess, continuous benchmarking practices applied to a spectral element library in Fortran. So I guess, yeah, take it away, Joseph.
Hey there.
See if we can
Let me go ahead and get this shared. Yeah, thanks for the introduction. So we'll just go ahead and I guess the overview here is I'm going to talk to you guys about a tool we've been working on to address the need for an application we're building to enable continuous benchmarking so that we can assess application performance across a variety of hardware. For those of you who don't know, I work at a small company in Boulder called Fluid Numerics. We're a cloud native organization. We produce software products that do make it up on the cloud environments. And so a critical part of delivering software to our customers is to identify the platforms that are going to give them the most cost savings. So this was absolutely necessary for what we do. So the Spectral Element Library in Fortran, it really for a long time has been a piece of software that we use really as a sandbox for experimenting on porting to new architectures. But it's turned into something a bit more since those days of sort of just playing. We aim to provide spectrally accurate tools for solving specifically hyperbolic conservation laws and complex geometries. It comes with a lot of pre-canned solvers for things like shallow water equations, Euler. We do have some parabolic operators in place, so you can add, your own explicit diffusion. So we are working towards Navier-Stokes at the moment. We also tried to build this suite of tools so that it can run on a spectrum of compute resources, everything from a laptop to cloud computing environments to HPC clusters. So we do support serial, parallel, and GPU accelerated applications. And we also have been working on a transition to get away from CUDA Fortran, to get more away from vendor lock on the hardware. So we've been working towards porting to ROCm and HipFort. And in terms of deployment right now, where you're shipping artifacts, including Docker and Singularity containers. And so when you mix, an application like this with, basically trying to support such a variety of hardware, we have to operate what we've been referring to as what's called an image bakery. And the idea behind this sort of concept is you want to go from source code on one side where your developers are sitting and get it shipped over to your users on the other side through an artifact registry or some kind of container registry. Usually this is coupled, at least in the cloud, with what we call infrastructure as code. So the necessary bits to create the compute resources on a cloud environment. Now, in between the source code and the artifact registry, to make sure users are getting something reliable and safe to use, we have a few steps that we go through. So we do have a build environment. So a lot of the talks this week have touched on various tools or even strategies just to implement to get your code built and tested before doing releases and things like that. The specific tool we opted to go with for self is Google Cloud Build for the build environment. For us, this choice was really driven by really just the flexibility that this framework provides for doing builds and testing, and even going as far as deploying complete systems on the other side. Outside of that build environment, we create those Docker and Singularity containers, and before we actually post them to a registry, we'll subject them to a bit of testing. So as I mentioned, those artifacts do vary. Right now, we do ship Docker and Singularity containers. For specific cloud platforms, there are also some benefits to doing virtual machine images just for the minor improvements in performance that you can get. So we're looking at those as well. Now, in the testing environment, and really the subject of what we're talking about today, is this little bit of tooling that we've added to our build environment called RCC Run. And if you're interested in learning more about that outside of this talk, we do have a tutorial tomorrow morning. So Cloud Build, just a very brief overview. It's a tool. It's a serverless CI/CD environment. It's very similar to what you might have seen with like GitHub Actions or GitLab runners. Of course, this one is just a CI/CD tool that's nested in Google Cloud. It is secure in the sense that all your builds run in a completely isolated build environment. It's flexible in the sense that every single step that you want to run to build or test your application, you can completely customize. And the way this is done is that each step is provided, is executed within a Docker environment. So if you have your own Docker images, you can create the own environments for doing various tests. So if you want to build your application with a certain set of tools, run your tests, create coverage reports, things like that, and upload those coverage reports to another service like CodeCov or what have you. All of those individual steps can be done in very lightweight containers that are managed by separate parts of your organization, or even pulled from a public Docker image repository. The other benefit as well, just like you have with GitHub Actions and GitLab runners, is there's the option to have automation built into your testing. So when you are ready for it, you can have builds and tests triggered based off of pushes of commits, tags, or opening of pull requests on a GitHub, GitLab, Bitbucket repository. And to get started with Cloud Build, it's pretty straightforward. As I've learned, as you start to get more into these kinds of systems, everything comes down to just defining things in a YAML dictionary or a JSON dictionary or HCL. For Cloud Build, all you really need to do is define what are called build steps. So at the very top here, let me get the laser pointer on. This is an example of where our tests were prior to actually doing testing on a variety of hardware with RCC Run, but a very basic idea here is we would build a Docker image. So, of course, in our repository, we'd outfit with a Docker file. Once you build that image, we can actually use that Docker container that we've created to run the next build step where we would run our tests. And after those tests are run, we would run like a CodeCov container to upload those coverage reports up to CodeCov so we can keep track of how much of the code we're testing during the testing cycle. Now, the deal is with this kind of environment and with like what you would get on GitHub Actions, you're very limited in the compute resources that are available inside of these kinds of environments. You also don't have the option to select what kind of CPU platform. So if you want to integrate things like benchmarking, usually when you're benchmarking, you don't just want to know the runtime. You want to also know, what CPU platform am I on? In the case of GPUs, which you certainly don't get with GitHub Actions and even with Cloud Build as it is, you want to know what you're actually running the application on. And then also, along the way, you probably want to tie this up with, what compilers you're using, what compiler flags you've applied, any target architectures you're going after, things like that. And that's really what drove the motivation for RCC Run, was just some of these limitations that a lot of these tools have in really just trying to get the information I think that, those of us who are in HPC really care about. So, I just want to step back now and think about like, what are the processes to doing this, in cloud? At least in cloud, we are working on extensions to get these integrations set up with on-premise, but at least in cloud, you have a few steps you need to go through in order to do this kind of benchmarking. So a very high level, all you have to do is create the compute resources that you want to run on. You run your jobs, you collect data, usually like runtime, how much memory is consumed, those kinds of things, and you aggregate that data and post it somewhere for later analysis, and then deprovision those resources so you're not continuing to rack up a bill on a cloud provider system. So the ways we decided to make this happen was using a few different types of tools that are available. Those of you who've been on cloud, you may be familiar with Terraform. For those of you who are not, essentially Terraform is a way for you to express in a very simple YAML-like syntax what resources you want to create. And the Terraform layer, so the binaries that come with Terraform basically handle all the API calls to any cloud provider. So it integrates with Google, Amazon, and Azure. And we've put together a module just to get started here that works particularly with Google to create a controller that hosts a Slurm job scheduler. And we decide, essentially to schedule our jobs and manage our workloads and get information. We'll take advantage of the information that Slurm already collects when you submit a job. From the cloud, and since all the tests are run from the cloud environment, you can't just directly run the jobs on the Slurm controller from cloud build. You actually have to issue commands over SSH to make that happen. So in terms of running jobs, we reduce that process into essentially doing what's called G-Cloud SSH, which handles SSH on Google's network. When those jobs are run, the Slurm controller will automatically spin up compute nodes on the fly, execute those workloads, and then we have some bit of a scripting layer that sits on the controller side to parse the information out of the Slurm account database. Once the jobs are done, all that information in the workspace comes back into the cloud build environment, and we load that data into a database. Now, there's a lot of options out there for how you store the data. We've decided to go with BigQuery, which is essentially the same thing as Google Sheets. It just allows you to have a lot more data. So if you're doing commits pretty regularly, if you have a lot of different code you're testing, it scales pretty nicely without getting like the bog down you would get with something like Sheets or any other data storage types on Google Cloud. And at the very end, since we use Terraform to create those resources, we can also use Terraform to tear things down. All right, so that's the general workflow that we need this tool to do and some of the bits we need to stitch together to make it happen. Now, in terms of integrating this into Google Cloud Build, like I said before, each step in Google Cloud Build needs to be a Docker container. So we packaged up, all right, so what is needed? We need that builder. So we need that Docker container that hosts some source code that manages all these different tasks. So that Docker container needs to have Terraform in it. It needs to have the G-Cloud SDK so we can issue commands over SSH. It also needs to have somewhat of a scripting layer to kind of manage that whole workflow. And for this, we've just gone with Python to make that happen. And of course, since we're using Terraform for that deployment, we need some way to be able to concretize and customize what compute resources we want to have available. I am going to go back one slide. The nice thing about cloud environments is you do get access to the variety of resources that are available. There's a suite of GPUs. You don't just get one GPU type. And there's a lot of different CPU platforms to choose from. And so in this section here where we're actually calling Terraform, you have the option to choose what hardware you want to run on, so long as it's available right on the cloud. And with the integrations we're doing now to get onto on-prem with whatever you have on-prem. So that's that last bit. It is an optional variable that you can add. Otherwise, the defaults out of the box just stick you on Intel Cascade Lakes. All right. So this next slide is might look like a lot, but every bit of this information is absolutely needed for what we want to do. So when you benchmark your code, you want some way, especially if you're talking about integrating. Benchmarking is part of a continuous integration process. What you need to be able to do is not just have the runtime for your application and what machine you're running on. You also want to tie that to a specific version of your code that was run on. So when we want to add, when we were thinking about designing the interface for RCC run, we knew we needed to at least tie in somehow to this aggregate of data that we're going to pull together to a GitShaw. You also might have, depending on how your team likes to do their testing or how you're thinking about doing it, for each commit you have, there may be multiple builds you're doing, and it might be for for different architectures. For us with Self, we do, for each commit that goes up, we have a Docker container that's built for AMD GPUs, one built for the NVIDIA GPUs, and then one built for CPU only platforms. So we actually have 3 builds that run every single time a commit comes in, and it's all tied to the same commit SHA. And so we figured at least having these build IDs that are generated by Google Cloud Build, we tie that into the database here. So, right. So outside of that, there's some additional information you need to attach through this system in order to deploy your resources. So if you're not familiar with cloud providers, the way they work, essentially all your resources are organized into, I think on Amazon it's called folders, on Google it's called projects, and on Azure it's called subscriptions. But there's a way to basically group resources that you're purchasing together for billing purposes. So, and when you go to deploy those compute resources, you do need to identify a project they go to. The rest of these arguments are really just there to help you tie up some of the necessary information to align with the benchmark. So again, what compiler are you using if you're trying to build for a particular target architecture? Of course, if you're testing a singularity image, you need to know the path to that singularity image when it's created, etc. But essentially, this was the only modification we had to do in the end, outside of course, us creating RCC run to add it to our cloud build file. Outside of that, we have tests that you need to specify. So when RCC run is executed from cloud build, what it's going to first do is going to go create the compute resources. And then it's going to figure out, okay, well, what tests am I going to run in your repository? So you do need to, like you have in any other testing infrastructure, define in some way what needs to be benchmarked. And you can think of it like in 2 levels. So one, every single test you have, we encourage folks to script their tests. Like think about what you would actually write if you were submitting to a Slurm batch scheduler, for example. And as long as you have that script and it's saved in your repository, you can reference that script in one of your RCC run tests. So the execution command would basically provide those instructions. So what you're going to send to sbatch for that run underneath on the cluster. If you had a custom output directory where if you wanted to do file, check the output of your application later on, you could direct that to a specific location so that when that information comes back after doing the benchmark, if you wanted to do correctness assessment on your model output, you could configure where that data ends up on the other side of running RCC run. The way you control what compute resources you run on is through Slurm partitions. So if you've been, most HPC data centers run with homogeneous clusters. So you'll go in, you'll have one group of compute nodes to run into, and they're all the same. Some groups do have access to heterogeneous resources where compute resources are divided into Slurm partitions, and we kind of take that model onto that Slurm controller deployment that goes up under the cloud, to where you can make available all the different types of CPU platforms and GPUs and organize them into Slurm partitions. So that when you're running your benchmark, if you wanted to run, for example, this same command across multiple instance types, all you have to do is, duplicate this particular test and swap out the partition. You can also add special batch options if you don't have them inside of that script. So if there's specific things you want to do, like, maybe change a GPU type through a gres argument or specify a wall clock limit for that specific test, you can do that here. The last argument here I didn't quite go over yet is the command group. So we found a need when we were doing these benchmarks for actually where we really got started with this was benchmarking Wharf and OpenFOAM and other applications that we were trying to integrate onto the cloud. And with like things like Wharf, you have, a few stages for deploying a benchmark. You might have a stage where you're creating the input deck, the initial conditions and boundary conditions. Then you actually have the stage where you're running the simulation. Then you have a post-processing stage where you might, if you did parallel IO and Wharf, for example, you would stitch together output and then do your analysis on it. And any tests that are in the same command group essentially have automatically SLORM job dependencies applied to them, so that you can have those three things happen at the same time, but you can still separate out in your benchmark database, whether you were doing that initialization or you are actually running the simulation. So it's really a convenience argument to help you organize how those jobs get scheduled and then how to sort them in that database on the other side where you have your benchmark data. Now, in terms of adjusting our scaffolding a little bit in Self, so what I mean by scaffolding is the directory structure we have in the source code. Of course, we have our source code is in a source directory. We've got a make file. We've got, Docker files, those kinds of things. So what I'm showing you here is the additional things we added to make this happen. So we added, just for keeping things neat and tidy, a directory we call CI. So at the very, very top here, there's a Terraform directory that contains all the things you need to it really just stands up that BigQuery database where that data is going to end up, since that is something that is long lived that you want to store for quite a long time. And then we have our wrapper script for running our test. So this is the singularity exec.sh. This guy is what ends up getting called inside of our RCC run YAML. We've, I showed you a couple slides back, what our cloud build pipeline looked like, that YAML file that told us what steps need to happen to build and test and create coverage reports. Rather than adding on to that, we chose to keep that one in existence and then add to it another build test that gets run for just doing the benchmarking. And the only modification there is, rather than running a serial test within the cloud build environment, this actually integrates with RCC run to run on larger compute resources, things with GPUs and the like. And of course, we add this RCC run.yaml, which again is this kind of file where we specify all the tests we want to run to exercise the various bits of the Self library and some of the example programs that come with it. And for completeness, I did say, you can specify a Terraform file for defining your cluster infrastructure to customize it. We needed to, since the default architecture we put into RCC run does not include GPUs. So we had to add this Terraform file. Now in the tutorial that we're going through tomorrow, we kind of walk through starting from, a Fortran repository with a make file and show you how to incrementally add these bits to help you get a feel for this kind of stuff. So, if this is something you're interested in, definitely check that out tomorrow. Now, the cool thing here is the end result of doing all this stuff and of course, adding the build triggers to basically when we open pull requests and certainly when we make updates to a develop branch or a main branch in Self, is we naturally start to build information about how fast each of these examples run. And depending on the examples, we know from our coverage reports what parts of the codes are getting exercised. So we can start to get a feel for how we're doing over time, especially as we make changes. We want to make sure we're not certainly getting slower on architectures we were doing well on. And if we are getting slower, we do try to use that as a motivation to take a deeper look. Now, BigQuery by itself is not helpful for just understanding what's going on unless you're really good at writing SQL queries. I'm not of that ilk. I certainly love to dashboard things. So with the information that we actually dump out from RCC run, which there's a lot that we collect, including exit code, standard out, standard error, you can dashboard various things as your code evolves over time. You can just get a quick glimpse of what's happening. So one way to use a lot of this information we found useful was to create what we call pass-fail reports. So it just looks at the last week of development and it just pulls together anything that had a non-zero exit code, and it surfaces STD out, STD error into the environment. Data Studio is quite a nice tool. It's absolutely free, integrates with BigQuery. And if you're familiar with dashboarding with something else like Grafana or what have you, it's very likely that BigQuery integrates with it. But it's just one example how you can use that information. Now, of course, achieving the original goal of trying to understand how we perform on a variety of hardware, this is where it really starts to shine. This is like a pivot table that shows each of the command groups. So the command groups for us correspond to a specific example integration test that we run. And it looks at along the columns here, the different architectures we run on. So here I'm just showing a comparison between like running on a V100 GPU versus a 4-core Intel Cascade Lake setup. But again, you can start filtering things by date, by commit SHA, or however you want to search through that data to understand how you're performing across a variety of architectures, so you can easily make decisions about where to deploy your architecture, what recommendations to make to your end users about where to run, how they should build their code, should they want to build it themselves, or which in our case, which containers we recommend using and on what hardware. I do have, I'm running out of time here. There's another use case that's out there in the wild. If you look up on GitHub under Fluid Numerics RCC apps, we did something a little bit different here. Rather than creating Docker and Singularity images, we create virtual machine images for Google for some commonly used research applications, including WRF, OpenFOAM, GROMACS, Amber. I'll skip some of these slides here, but the general idea is we can integrate that same tool into these kinds of platforms to do the same kind of dashboarding, so that we can identify, again, where these commonly used research applications would perform well on GCP. So I'll go ahead and leave it at that and open the floor for questions. Oh, right. Don't forget ISS tutorials tomorrow at 9 a.m. if you're interested. If you missed that, the code lab and demo code is all available online.
Great. Thank you so much, Joseph. Let's give him a virtual round of applause. So thank you very much. And let's now let me see if anything's coming to Slido. Not yet. Well, I guess I'll kick off the questions first. So you kind of mentioned, like, I've never used RCC, but how detailed in terms of the architecture can you get? Like, because you kind of mentioned like specifically like Cascade Lake and V100. I mean, can you specify the exact, like, I want NVIDIA V100s and I don't want.
Yeah. So on the GPU side, you have everything from K80s up to the A100s available. On the K80s up to the V100s, you can have up to 8 GPUs per node. For the V100 architecture, if you're on the 8 GPU systems, they do have NVLink between the GPUs. And if you're on the A100, you can go as high as 16 GPUs per node. So they're on the HGX boxes from NVIDIA. So it does give you quite an array of platforms, at least on the GPU side, to play with. We've been experimenting with doing what's called a federated deployment. So where we actually have what we call it an RCC, a research computing cluster that sits in Google Cloud. The controller sits there permanently, and it's actually connected to a controller we run on a dumpy little Dell box that we picked up from an auction. And we connect it to a node with an AMD MI25 on-prem, and you can actually get those talking together. So if you have other resources on-prem, the RCC tool that we've developed can connect to an on-prem system and really just enhance the resources you have there. So even if you find like you're doing CI on-prem, and it's just eating up compute resources for other activities, even bursting the other way into the cloud for some of your testing could be a good use case there. But on the CPU side, you have AMD EPYC Milans just came out recently. There's Intel Cascade Lakes. Both of those are what they call their compute optimized instances. And then you have a whole array of what we call general purpose nodes. So you have everything from Intel Broadwells through the Skylake range on one side there, and then they also do have the AMD EPYC Romes, the previous generation from the Milans.
Oh, that's great. Yeah, thank you.
Yeah.
All right, and now it looks like we have another question from David. What kind of scale have you seen in deployments? Like how many nodes, build types, etc.?
So I'll tell you the biggest we did with RCC run with Wharf, we got up to 11,000 vCPU. And those were on like, they were on the C2 standard 60, so it was 60 vCPU per node. So it was in the order of hundreds of nodes that we got up to. We started to run into issues where we had to do like multi-region deployments, at which point like the communication latency just tanks because you're trying to communicate between data centers. But it is doable, and we did find like, at least if you're in like the 1,000 rank range for Wharf, things do scale pretty well up to that point, which was pretty surprising to us, considering, you know, cloud environments in general have higher latency network. Their networks have higher latency. For most of our testing with Self, we are, since we're GPU accelerated, we try to stick on what we call a fat node. So we cram as many GPUs as we can on there, because once you go off VM with GPU communications on cloud, the scaling is pretty terrible.
That probably speeds up the test run time significantly, being able to scale that much.
Oh yeah, significantly, because that's the other side of this too, is we actually had to dial back rather than benchmarking every commit, which is incredibly expensive. We have benchmarks that are run only on pull requests now, and we've had it set up to where you like an owner of that repository has to run a / command in order for that to happen. Because the bills for running these things as often as we commit, it was just getting out of hand. And I think that's, you know, the one side of like doing on-prem work is a lot of people don't see that direct cost. But it is there, and certainly I think people feel it in other ways on-prem, like, you know, just resources are consumed and other work can't be done. So yeah, speeding up that runtime definitely helps, but you do got to be careful.
Great. Just one left comment, just saying like, thank you, Joe, for the great talk on Slido. Otherwise, I think we are out of time today. So thanks again, everyone, for the presentations. And for everyone else, we'll be back on in around 12:50, I believe. So thanks again, and have a good lunch break.
Welcome back, everyone. We'll be starting this afternoon session for today. Leading the second talk today is Samir Shende. He'll be speaking on the E4S stack and extreme scale scientific computing. So go ahead, Samir.
Thank you for inviting me today. I'll be speaking about extreme scale scientific software stack, or E4S. And the key problem that we are trying to address here is that as our software gets more complex, it's now getting harder and harder to install our tools, our libraries, correctly in an integrated and interoperable software stack. The E4S project aims to address this issue by providing a curated SPAC package manager-based software distribution of a large number of HPC and AI ML packages, and it includes runtimes for GPUs. It supports Intel One API, NVIDIA's CUDA with NVHPC, and AMD's ROCm. So you can use the same software stack across all 3 GPU vendors. And it also features build caches, which have binaries for SPAC, and also containers. You can find out more about this project at the e4s.io webpage. So as I mentioned, it's a curated SPAC-based software distribution. And we target x86-64, PPC-64LE or IBM Power 9 systems, and also ARM64 or AART64 systems. We have container images that are available on Docker Hub and E4S website with both base images so that you can create your own custom containers and full featured containers. And we have also recipes on how we create these images. And we have integration with GitLab, a validation test suite to verify that the packages are installed correctly. And we have a virtual box image if you're just starting out with containers, want to learn more about these different HPC runtimes, and also images on the commercial clouds such as AWS or GCP. Now, the three main areas of the exascale computing project include application development, software technology, and hardware and integration. And there are over 70 software products from this project. And as you may be aware, our roadmap for exascale computing includes systems that have GPUs. Our current generation systems include Summit and Sierra, which have NVIDIA GPUs. We have Perlmutter with A100 NVIDIA GPUs, and new exascale systems that are coming out online, including Frontier, Aurora, El Capitan, and Crossroads. So our goal is to build a comprehensive, coherent software stack that enables application developers to be more productive on these HPC platforms. And there are several technical areas. We have programming models and runtimes, development tools, math libraries, data visualization, software ecosystem, NNSAST, and also workflows. And they have a number of packages that you may already be using. These include MPitch, OpenMPI, numerical libraries such as PETC or Trilinos. We have node-level parallelism supported by Cocos and Raja. SPAC is the package manager and the core technology that's being used here. And we have a number of emerging packages as well. You may have used performance evaluation tools like PAPI or Tau or HPC Toolkit, LLVM compilers, IO libraries like HDF5. They are all part of the E4S. And we use these software technology products and group them in logically related products or software development kits, SDKs, that then are assembled together to form the E4S distribution. We have an aggressive quarterly release schedule. We just had a February 2022 release, or 22.02 as we call it. And there's a number of different components, including our community policies. So if your product wants to join E4S, how can you do that? You can just go to our webpage and check out the policies. These are community policies. They are simple policies like you should have a test suite, you should have a SPAC package, you should have an entry in the doc portal that we can help you create, and so on. And then we assemble these products. And starting from our first release in October 2018, we have come a long way, and now we just have E4S 22.02, which has 100 full release products. And as I mentioned, it uses the SPAC package manager for software delivery. But SPAC is not just the package manager for E4S, it also includes a large collection of software tools and libraries outside of the exascale computing project's software technology. And the reason we use this is that scientific software is becoming extremely complex. The dependency graph that you see for, say, NALU, which is a generalized, unstructured, massively parallel, low-mark flow solver package, a CFD package. And you can see that NALU depends on Trilinos, which depends on Parmedis, Metis, it depends on MUMPS, Netlib, Scalapack, OpenBlast, and a number of components. And you have to all assemble these components together correctly for the package to run. And the dependency graph just gets more and more complicated. This is DEAL2, a C++ finite element library. This is the graph of RMiner. So you get the idea that as the number of packages increases in our applications, it's getting to a point where it's very difficult to build and assemble these packages. Even proprietary codes, such as Aries, depend on a large number of open source libraries, which are shown here in blue boxes. And we are, in fact, building an entire ecosystem of over 15 applications with over 80 software packages targeting multiple platforms, compilers, programming models, and versions with external dependencies. And if you just see the explosion, you'll see that it has over 1 million combinations. And each application has its own stack of dependencies. And we are at a point where there are developers, facilities that are now dedicating several FTEs to just building and porting these packages. And they often trade reuse and usability for performance. So we must make it easier to rely on others' software. But how do we install software on a supercomputer? We start by downloading all the tarballs for all the packages and start building them one after the other. And it's not easy. We fight with the compiler, we fight with the configure scripts, we tweak the parameters, and finally we assemble a binary which links all these packages together. And when we run the code, it may segfault and we start all over again. So there has to be a better way. Now you may say, what about modules? Well, modules just set environment variables such as path or LD library path. They don't install the packages that somebody else has already installed. They just provide environment variables that allow you to access them. So SPAC is the flexible package manager, and it comes from LLNL. You just clone the SPAC repo like this. You can source it, and then you can just install a package. You can say SPAC install tau, and tau and its dependencies are installed within the SPAC directory. The important thing to note here is that SPAC can install many different variants of the same package with different compilers, MPI implementations, and even build options. I typically start by saying SPAC compiler find. So set up compilers in my environment to use the system compilers. I can say SPAC external find to find other packages like tar, CMake, or M4. And then I can say SPAC install tau. But I can be more specific and say, please install SPAC. Please install tau version 2.31 using the @ operator. Or with the percentage symbol, I can pick a compiler that has been previously found by the SPAC compiler find. So I can say, using the GCC compiler version with the @ 9.3.0, or enable options like plus ROCm for AMD GPUs, or enable MPI, but please use MVAP H2 version 2.3 without the wrapper RPath option. So you can make it very specific to your specific needs. And then you can say SPAC find, and then it will show you all the packages that are installed. You can learn more about SPAC and how it's enabling the ECP software strategy at the spac.io webpage. Now, in the ECP software technology area, we have support for many different applications. And there are many products from ST that these applications rely on. And if I look at these packages like tau or flux or papi, they are used by multiple applications. And you can see the different areas of the software technology which are represented here with the legends over here. And we have programming models and runtime SDKs that have logically related packages, compilers, and support tools and technology. I lead the SDK area for the programming models and runtime, and other areas such as data and Viz and ecosystem at large, and XSDK or the math SDK. And we use these SDKs to build the full E4S distribution. So again, to recap, we have a curated collection of these packages, and we also have container images. So we have base images and full featured images that support GPUs. What are containers? Well, a container is a lightweight collection of executable software that encapsulates everything needed to run a single specific task. The important thing is it does not include the operating system kernel. So if you look at the different options, whether it's a type 1 hypervisor, where you have a full virtual machine running with its own operating system, or a hypervisor running on an operating system where there are 2 kernels running, containers are relatively lightweight, and there is no second kernel running here. There is no kernel of the operating system. It just uses the host's operating system. So containers provide a viable way for bundling all the packages and then providing it in a distribution that's easy to deploy. We have a minimal stack image on our download page with mirrors, of course, with Docker and Singularity images. We have GPU base images, so you don't have to start with a full featured image. You can start with an image that includes support for NVIDIA on multiple platforms like x86, ARM64, and IBM Power 9. Or you have ROCm, AMD GPU support, or Intel One API for Intel processors as well as GPUs, and other continuous integration images with different types of RHEL and Ubuntu packages that are supported. This is a base image. It is quite popular. You can see it has over 1 million downloads. And this is the container page where you can download the Singularity image. Now, this full featured image, as opposed to those base images, has support for all 3 GPUs in the same image. And it has support for compilers, it has support for runtimes, and 100 different packages. And these are GPU runtimes like ROCm, Intel One API, NVIDIA, CUDA, NVHPC, and they are all in your path. These are the locations of the 100 packages. They have packages like MPage or Amrex or Hefty or HDF5. These are packages you may already be using. Packages like Parsec, ParaView, Tau, Trilinos. You get the idea. We also have languages like Python, Julia, and AI ML products with GPU support. And yes, if you have, say, an NVIDIA GPU or a AMD GPU, you can use TensorFlow, PyTorch, these packages with support for the GPU directly. It also has support for X applications in the container. So you can run tools like ParaView, Visit, or Paraprof from Tau. This is what we have for IBM Power 9. And you can see the different 100 packages there, and the full featured GPU image for Docker or Singularity for different architectures. We also have an LLVM image where we have built packages using the LLVM compiler. And you can download this directly from Docker pull by just saying Docker pull and our ECP E4S. Now it's interesting that you can build your own application using these images. And you can then access the GPUs as well if you use the full featured image. Here is an example of Tau support for NVIDIA GPUs. And you can see that we have architecture SM80, which has all these packages built for A100 GPUs or V100 GPUs. If you just launch Python, you can import TensorFlow, PyTorch. You can even access the NVIDIA SMI and other tools which show you the versions. So with this, let me just say that, how do I use this? If I have a Docker file, I can say start from this Ubuntu latest image. I want to add this hello world.c example, put it in the app directory, source the setup.env.sh, and load the mpich package, and use mpicc to compile this hello world.c into a file called app hello. It's as simple as that. We start with something like, here is the hello world.c, and it's just printing the rank and the MPI com size. And you want to use a container. So with this, what you can do is, we have steps of how to create a container. And you could just start with something like this. You could just say, you build Docker build command with the tag my hello MPI and latest. And once this is done, it will copy the hello world.c into that directory called app. You've started with the base image, Ubuntu 18.04, and then you've created your own container. Now with this container, you can then say my hello MPI, and you'll see that this image is there. then you can say docker run rm-it and give this name of the tagged image. And now you're inside the container. You're in the Docker container. If you go to the app directory, you can see that there is the hello world, and you can just run hello like this. And your application is ready to be deployed on a container. You can just push it with a Docker push and give this, and then make it available to someone else. Similarly, you can build a Singularity container starting from our base images. So this provides a very useful way for you to pick what is already provided and build upon that, add your application, create your own containers. And with that, you will be able to use the GPUs. You will be able to try accessing different runtimes, even AI ML packages. And then you can look at how we have built the full featured image. Here we have different variants, like for Trilinos, we enable all these solvers in a file called spac.yaml. And then these are the variants for the various CUDA specs. And we have built it with ROCm for MI100 as well as MI250X AMD GPUs. We have built packages using one API. And we have binary build caches to speed up your installation. So if you just use this spac add mirror command, and when you say spac install a package, it will just pull in the binaries from our build cache, which has over 80,000 binaries. You can also have a look at our AWS image and see how to build it. I was in fact using the AWS image when I was showing you this Docker command, but it has support for different visualization packages. This is Tau. This is a profile file that I've opened up. This is ParaView and other packages that you can just launch like this. There's a range of different packages, and it's a full software stack that's ready to use. We have a virtual box image that includes SPAC. It includes all of these different runtimes as well. And we also have a tool called E4S Container Launch. It's a tool to simplify the launch of MPI jobs in E4S containers. So if you have MPI, say from MPitch, we can use the MPitch ABI to replace the MPI with the system MPI. So you could have efficient internode communication. And we support both MPitch variants as well as OpenMPI using the Y4MPI package from CEA in France. And this E4S CL tool allows you to just pick your MPI on the host, specify the backend of Singularity, specify the image, and say, when you start up the image, these are the commands that you should execute in the source.sh. Then you can run this application with a different MPI. So I could build with MPitch, and then I could run with Intel MPI or OpenMPI. And this is the architecture of the container launch tool from E4SCL. We have recipes for building, just like I showed you how to create your own application Docker image. You can create such recipes using SPAC and use this spac.yaml file. And then you can tweak your own recipes. We have support for multi-platform reproducible Docker recipes. These have sped up applications in ECP, such as the WDM app for the whole device modeling for ITER, Reactor. This is the Pantheon project at Los Alamos National Labs that is using E4S to build up their applications. They have reported over a 10 times speed up in using E4S. And we also have a validation test suite. Now there's a number of solvers, number of packages. It's not enough to just compile them. We need to make sure that once we have installed the package, we can run some example. So we have tests where we have a validation test suite, and in that every directory, this is the directory for Magma, has a compile.sh, clean.sh, setup.sh, run.sh script. And then you can just sweep through a large number of these packages together to verify that the whole distribution is installed correctly. So I would like to just say that E4S is an extensible open architecture software ecosystem that does accept contributions from our US and international partners. It's a framework for collaborative open source product integration. It's a full collection of software capabilities. I can think of it as a vehicle for delivering high quality, reusable software products and a conduit for future leading edge HPC software targeting the scalable next generation computing platforms. So our vision is that it has emerged as a new top level component in the DOE HPC community that allows us to build new relationships with US agencies, industry, international collaborators. We have a portfolio that can expand into new domains to support AI and ML more effectively, lower level components. And it hopes to deliver better, faster, and cheaper software integration. Our work at the University of Oregon, we have several partners, but our work at the University of Oregon is carried out at the Performance Research Lab. And this is the University of Oregon campus. And I would like to thank our funding sources and especially the Exascale Computing Project, which has supported the E4S project. For the hands-on, I showed you the container launch, and we have these tutorial examples. So I can launch a container image like this, and you can see NVIDIA SMI, can access the GPU. I can say SPAC find, and then I can see all the packages that are installed. I can say SPAC find -DL-V for data dependency listing, and the verbose option for a package like Trilinos. And then you can see how it was built with the different solvers. And here it is. And you can see how the package was configured, what options were used for building that, and the dependency tree. Here in the application, here I can say run E4S cl.sh, and I can specify Intel MPI and then or mvaph2 and then specify the image. I can look at the source.sh, which shows you how to load this Trilinos. And if I have a binary which was built with the container, I can just run this like this, and then it will use the Intel MPI instead of the MPitch, and then it will find the libraries for you which need to be substituted, and it will run the application like that. So I'll take a break here and ask if you have any questions on E4S.
Thanks, Samir. We have a question in Slido. I can read it out loud for you, but the question is, when I build my own container, my image size increases quickly at the order of gigabytes after multiple packages are installed, e.g. different compilers, MPI libs, etc. Does E4S constrain the image size, or does E4S have a way to reduce the image size for quick download and deployment?
That's a very good question. We have images of different sizes based on how many runtimes you choose. And there are ways to optimize your image size. One of the things here is the execution of the application, but here is the example that I was showing. And in the Docker image, you can start with this, and then each of these run commands creates a layer. So it's better to chain those using the and operator and do the cleanup before you exit. That will reduce the size of the image considerably. You may want to just keep the image. If you are creating an image using a Docker commit or save, you can keep that image around and tweak it, and then just take a copy of it with the Docker commit command, and then you can also optimize it in that manner. But it's a good idea to remove the packages that are installed, do a make clean after the installation is complete, and reduce that all within the Docker recipe. So we do not constrain any size. You can have an image of any size using one of our images. So if you go to the E4S project page, you can find all of the instructions for creating your image or pulling our images with minimal or GPU base images. The full featured image has all 3 of these GPUs, so it will be a little bigger. Did I answer your question?
I believe so. If John wants to follow up, he can. Sorry about the construction of my audio. One other question from Josh Brown. If E4S is an extensible ecosystem, is there a set of guidelines for or standards that they require to add packages to the ecosystem to ensure the software quality is maintained?
Yeah, absolutely. And this is documented in the E4S community policies. And these policies allow us to ensure that the software quality is maintained and that there are validation test cases that are provided. We just want to make sure that your package does what it says it should do. And we want to make sure that it is correctly installed. We will work with you to make sure that the output is as you expect it to be. And then we have a team that will add that project to your to our doc portal that can be used to identify what that product is, and it rakes the repos, the Git repos from GitHub every night. So the data in this doc portal is very current, and you can search for different tools like Tau over here. And then you can see the options for different tools. Did I answer your question? Said you mentioned a process for others to participate with and contribute to E4S by use of Stack. Can you clarify further that process and how E4S supports specialized software needs at other HPC centers such that E4S can work well alongside in-house software stacks? Yes, so we support both bare metal installation as well as containerized distributions. So if you just download a single container, you can easily get this full ecosystem of 100 different products installed on your HPC site, at your HPC site. But you can create a new package in SPAC. You can create a pull request that gets merged, and then they validate that new package recipe. And you will be able to then participate, make sure that you're adhering to these policies, discuss with us, and we'll add your product to the E4S distribution. Does that answer your question, Daniel?
Yeah, thank you. I appreciate that. I think we're right at time. So any further questions, feel free to follow up with Samir with any additional conversation you'd like to have. Otherwise, we'll move on to the second half of the tutorial. I believe I'll let David take over from here.
Thank you very much.
Thanks, Samir. And so we've got David Rogers doing 2 of the 3 R's, in this case, refactoring and reproducibility. And then we'll have some time for general Q&A and discussion and hands-on activities and things like that. So take it away, David.
Thanks. Yeah, we started off today with a couple of segments of the BSSW tutorial, and then we heard from Joe Schoonover from Fluid Numerics on the topic of continuous benchmarking in the cloud, and just now from Samir on E4S, and all of these are kind of related as awesome tools that you can think about digging in and improving software quality and using those as ways to kind of make your development process more fun and easy. The things that I'm going to talk about today are specifically refactoring scientific software, followed by reproducibility. They're the things that all of us in this conference kind of take near to heart. The things that I'm sharing are slides that you can find on our website, and if you get inspired by these and want to take them back to your project teams, I encourage you to grab those slides and do a similar presentation to get people that you're working with on board. Here's our preferred citation for the slides. For refactoring, we'll jump in. What is refactoring? It's a discipline technique for restructuring how your code works without actually changing the external behavior of your code. So think about a code that's already working and it's doing what it's supposed to do. However, you want to do a little bit of restructuring and tweaking inside of that code. Of course, in order to do that, there's a whole bunch of steps that you have to go through. And this tutorial is going to give you some language and ways to explain what it is you're doing and how and why. It's also really important to start with a baseline because you have a working code, you have the ability to create that baseline for comparison as you move forward with your process. Why would you want to do all of this work if it's, as I say, it is hard work? Well, you want your code to be modular and you want to be able to work with it and show it to others and explain easily what it does. And a more modular, more well-defined and kind of better structured code is great for that. It's also important if you're adding new functionality or porting to new platforms to really take a good look at how your code is structured and make sure that it's ready to expand. I know that when I develop things, I generally start with a single file and then I restructure it and I add more and then I restructure it and I add builds and then I restructure it. And every time I expand it, there's a restructuring phase. So I'm going to walk you in this presentation through a couple of workflows, through this workflow a couple of times, some different projects. And I think we kind of are familiar with this as developers. There's, starting with your existing code and, having a good starting point. Doing a little bit of development and then using a regression test. So the testing phase is really going to be important when you're refactoring, having good tests and knowing where your code is at. Doing something incremental enough that's small enough that usually you don't have to do too many cycles through the fix before that one piece of your refactor gets done. Of course, once that one piece is done, you're not necessarily done with your entire refactor. If you have a large refactoring to do, there might be multiple passes through this loop. But when you're pretty sure that you're done, you still have to think about doing some integration tests and adding on top of what you've refactored now, take it out to the world and look at your customers and your downstream people who are using your code and make sure that their work is integrating with what you've done and everything is connected pretty well. And of course, you can celebrate when all of that's done. We have a running example that we're using for walking through our BSSW tutorials. It's a simple one-dimensional diffusion or one-dimensional heat diffusion equation, and it's simulated in a time-dependent manner. And you can imagine a refactoring exercise where you have one big monolithic file that has all the functionality just thrown into one single source code file. A lot of us have seen projects like this, or if you're building a new software, this is how they start out. And what you really want to do is kind of build a modular version where you have individual pieces of functionality kind of isolated from each other as much as you can, or as much as is feasible. In order to get into that refactor, rather than just diving in and digging in and starting to do things, it's important to think about what's your starting place and where do you want to be. So in a simple, in our simple example, the starting place is that we have a code that's doing what it's supposed to be doing, but it's not structured perfectly. And what we want to do is our definition of done will be that the code is, the refactor is complete when it's no longer monolithic. We have reusable smaller pieces. And it's a little bit easier to see how to test our code. So let's see, now that we understand what our code is going to look like once it's refactored, we'll have modular pieces split out with a cleaner and more maintainable code. We're going to think through some steps to get there. And these are the actual steps that we'll divide as our one cycle through the refactoring process. And for this one, it's going to be separate out the utilities. Those are going to be the easiest part to isolate because they're not super connected to all the code. Then we'll start on the difficult parts, which are putting the global definitions into a header file, kind of starting to break off into a header and library-like structure. And then we'll have to do a little bit of work with the build chain to make sure that the build process is working. Of course, it's important to really think carefully if you're proposing to do new code or intrusive changes. Usually you don't want to do those as part of the refactor because the refactor should change your code around so that it's still working, but it's structured so that you can add onto it later. Now, cost estimates. If you're planning your refactoring this way and you've talked to your project team and you know exactly what you want to do, you're in a great place because you can start to think about cost estimates. And these cost estimates are things like how much time is it going to take to actually change pieces of the code around, but also how much time is it going to take to run the tests and to fix unexpected glitches, which can be hard to anticipate. And also, how should we do integration tests? And are we going to have to add more documentation? And all of that should go into your estimated timeline and cost for doing the refactoring exercise. You also want to know how much change you can expect in your behavior of your code, because sometimes refactors don't come out with bitwise identical reproducible results from your original version of the code. You might end up in your refactor with a better version of the code, but you also have to have a way to compare it to your old version. Right, so incorporating testing overheads is one of those hidden costs that sometimes you don't think about. You think, well, I'll just go and change things around and it'll work. But making the tests stay in sync with the code is really important so that you know where you're at and that you can make it an incremental process. And so it's important to put those in. You might want to just go ahead and add 50% to whatever cost you estimate, just because you will run into unexpected glitches with your tests. All right, so rather than refactoring a monolithic code and taking you through those steps, I'm actually just going to give you a really simple, smaller example, because if I do that, then I can get through it in a shorter talk. In this smaller example, what I'm going to do is look at two different time integration schemes, the finite time difference scheme and an upwind integration scheme that's upwind, right? So you're looking on one side specifically so that you get a better numerical behavior for certain kinds of problems. And what I want to do is do a refactor where an original code, which has two different functions that do a time step with FTCS or a time step with upwind, can be written as if they're the same function with alternative options in the code. And so that's kind of interface work, so that the interface to the time integrator will behave similarly as it's seen from the main code. Here's where we get to do a little bit of work on the baselines. Before starting the refactor, you've got a working code. So go ahead and run, take stock of what tests are there, run your tests. And here's a picture of what happens if you run with code coverage. If you're using GCC, it's got a dash coverage flag that's built into it. And when you compile with the coverage flag, you'll get some cryptic gcov output files. And when you link with it and you run the code, it will actually output these files on the side, which tell you in text mode what lines of the code were exercised and what's your code coverage of the runs that you just performed. And so if you're running tests, then you should be able to get this coverage report after you've compiled this way. In this case, what we're seeing are lines with these pound signs that are telling us some of the lines of the code weren't exercised during our testing phase. So that's probably the first thing we need to fix before we start refactoring. And in order to enable those, in this code specifically, you just have to run the code and give it the option, say, to tell it, I want to use the upwind algorithm so that I've tested both of the two algorithms that I want to work on in my refactor. Okay, so you've done that. We now have baselines for both of them. We're ready to start fiddling with the code. We've talked a lot already, and we've seen people in this conference tell us about the Git workflows. So get your Git workflow ready to do some work on a branch. Look at the starting code, and in our example, we've got function calls to do a time step on FTCS or upwind integrators that are slightly different in the way that they're called. There's also a Crank-Nicholson, which is a third integration scheme. And so in order to have a code that's going to be able to call all three of these, you want to think, what's my interface going to look like after my refactor, and how do I turn these interfaces into something that's identical? Your programming team may want to use classes, or may use some like high-level data structures to pass back and forth. In this case, we're going to do a simple thing, which is just give every function call the same arguments. And so there's like an extra workspace here for Crank-Nicholson that's initialized. So what we'll do is we'll have everything get the extra workspace and everything get initialized. But if we happen to be using FTCS, then we just won't use the initialization or the extra workspace. Okay, so to generalize it, we just pick out this interface that we're going to make everything use, and then modify the makefile to have three separate ways to compile, so that the main program can either be compiled with method 1, 2, or 3. There's other ways to do this, and your project team will have its own kind of preferred method. But this is just the general idea of taking the same interface, so that so that your main code doesn't necessarily have to know what it's working with. So you've encapsulated it that way. Okay, so now that this refactor is done, the main code can now be compiled and run with each one of the two different integrators that we want to test, and we can verify it against the baselines. At this point, you might also think about testing to make sure that your test will fail before you've put everything together, so that you're actually testing something the right way. And actually, that's kind of the end of this example, because we'll assume that you've implemented everything correctly and the interfaces are compiling and working, and you verified against your baselines. Okay, so on to a more complex example. This more complex example comes from Anshu Dubey's experience with the refactoring the Flash code. And in the Flash code, the Flash code is a multi-physics code that deals with stellar phenomenon like exploding stars, and it's got the same kind of stuff that you'd see in the same kind of mathematical techniques that you might see in a climate simulation, where there's an adaptive mesh with flowing quantities moving over that mesh. And in this refactor, the purpose of the code was to take the adaptive mesh refinement library paramesh and allow Amrex to be used as a swap-in replacement. So this is, again, looking at those interfaces and figuring out what do we need to do so that our code can use either one of these two as its provider for adaptive meshes. Just getting to a diagram like this and that shows the structure of your code, shows what parts of your code are using this library, and what we need to think about as the interfaces between these. It is not actually a trivial exercise. And so if you're considering a refactor, it's really important to start talking with your team about how is the code structured now, and how would we like it to be structured after the refactor, and to spend time building these sorts of diagrams, which are also great for documentation, by the way, because it's really hard to auto-generate a diagram of how the code is used in practice and what's calling what, but it's also really valuable. Okay, so in this instance, all that's done for us, and we have a nice picture of what we're doing. Let's move forward with the planning phase. This is a picture of the end result of the actual steps that we went through that were involved in the refactor here. And the initial estimate took about 6 to 12. The initial estimate was 6 to 12 months, but it ended up taking about 12 months to get all of the pieces of this refactor done. And in the cost estimation, important things were, how much developer time are you needing to get it done? But also, who are the users of this code, and can we get buy-in from them on, are they willing to wait for this feature, or are they willing to deal with the disruption in the way that they're running, because this code is a production science code that's impacting people's careers and need it to be available. So anyway, working with your stakeholders and understanding kind of the context that your code lives in is important for designing refactors. All right, there are a couple of ways to get from here to there. Once you've decided we're going to refactor, and here's the beginning and the end point. It may be the case that you only have to make a whole bunch of small scattered changes, and in that case, it might also be okay to make a bunch of independent changes. However, in larger cases, you usually run into the difficult problem where parts of your code depend on other parts of your code, and you might want to refactor one or all of those parts. And in that case, you don't want to make a large-scale invasive change, because what you'll end up with is a halfway working code that you can't quite explain what is working and what's not and why, and pieces of the code might not work together. It's a great idea to make the changes as small as you can. So what do you do in this case? Well, what the Flash team ended up doing is two different plans. The first plan was to turn off all the modules except for the one being refactored, and then make a kind of have an intermediate way of working on each module in isolation, or as if it's in isolation, so that you can refactor the modules independently. This would work great if you're refactoring this module and you don't necessarily have to change too much of its interface with the other modules. Sometimes you change both the modules and their interfaces, so this becomes a little bit more difficult to do. So on-ramp plan 2 can show up where you might go one at a time and say, I'm going to change this module, but put it into a test environment where I can kind of change the environment to look like what I eventually want it to look like while I change the module. And then we can move this module. We could also, okay, so that the color of this box is changing because the way that the refactor was done, and I'll show it in a second here, was actually to make this module that's changing able to work with both kinds of environments. So it's a little bit more involved. But in any case, you can imagine doing this for multiple modules, kind of moving them through a test environment where it's easy to change the module and where you know kind of how it's interacting as you change it. All right, so how does that work out in practice? Requirements gathering. What is, so now you've decided you have a great idea of how your code's going to be refactored, but you're staring at this new library and you're wondering, how do I get my existing library to look like the new library? Or how do I get my code to work with the new library with completely different functionality? So requirements gathering actually became something that took a significant amount of time, just asking, what actually needs to change. And in the case of Amrex versus Paramesh, the big thing that Amrex does differently is that it doesn't have a really well-defined notion of boxes that live directly inside of other boxes. So you have a coarse grid and a fine grid, and the fine grid might live inside a coarse grid box. But with Amrex, there doesn't necessarily have to be that relationship. And so the way that Amrex loops through all the grid points is by doing iterators. So in order to kind of make the Flash physics modules work with both kinds of meshes, the team decided, hey, let's just make everything work with iterators because it's the most general strategy and it should work with both kinds. Now that that decision's been made, they pulled out just the simplest, smallest hydrodynamics code of maybe some advection, and use that as their guinea pig for how do we make it work over these meshes and iterators. And so they built a nice little iterator interface and used that iterator on top of a simple hydro code. Luckily for the team, they had an existing arsenal of tests, and everything was able to be tested as they did this. These iterators, of course, weren't iterating directly over Amrex yet, but they're iterating over the existing mesh provider. So it's kind of just adding some iterators in between the hydro code and the existing mesh. Okay, so now that step's done. Let's work a little bit on Amrex. Amrex provides some good high-level functions, but they're not the same ones that the code is used to. So the Amrex had to have an extra API layer built on it, so that the code could do things like Halo exchanges that it was used to without changing the way that it's actually calling those interfaces. So some extra API was added to the provider library in order to make the use cases much simpler to port. So far so good. Now it's time to actually put the two together and do something real. So the simple hydro was switched to something from the code that was turned off a lot of functionality, but was the smallest, kind of simplest unit where they could see an end-to-end run. And of course, they could use their existing tests, and they brought in this Amrex plus Grid API. or kind of worked on the driver so that the grid API looked as much as it could, as closely as it could to the existing driver API that was used. And finally, a little bit more was added to the MREX API, and more features were turned on. And at that point that they had kind of bridged the gap between these two codes and successfully gotten some use cases. And that doesn't mean necessarily that everything is done, but getting that first example down and working was a big success, because now they can kind of take that same pathway and widen it out to all the other parts of the code. All right, so summary on refactoring. When you're thinking about refactoring, have a really good idea of why you're refactoring, what your target is. If you want to make it more modular, what's going to be more modular? What do the new interfaces look like? And then plan for stepwise incremental refactoring tasks that get you there. And include in those planning costs how you're going to work on testing and how you're going to verify it. And it's really important to get buy-in from stakeholders. I also want to note that having those kinds of plans is great to be able to coordinate your team around refactoring work. I have a couple of minutes for questions on refactoring. I don't know if I want to, I guess I can stop and answer a question.
I don't presently see any questions in the chat, but welcome to pause a little bit more for people to pose some questions.
Okay, well, I'll assume that everybody is browsing through these slides and thinking about things, take home points that they can go and share with their teams. And I'm going to move on now to improving reproducibility through better software practices. We've talked in this conference a lot about different software practices that people are using, and I'm going to talk about reproducibility as kind of one of the big motivating driving factors that is really helping us to focus that work and get a clear idea of why it is that we're building these tools and what we're accomplishing with them. That's great and is building our ecosystem better. Here's our preferred citation format. I can start this one with the brief look at terminology. There's just a couple things I want to note. First, there's a lot of different words that mean slightly different things and help you wrap your head around reproducibility. For the purpose of this talk, all these slight differences aren't going to be super important. But if you're going to read up on the scientific reports that came out of compatible reproducibility taxonomy or the National Academy of Science report on the importance of reproducibility and replicability in science, you might run across the terms reproducible and replicable. And I should note that they mean slightly, that they're meant to mean two different graduation, gradual increasing strictness requirement on reproducibility, but their definition has changed over the years. So there were two communities that used them in exactly different ways. And so if you look at literature that's maybe a couple of years old, you might see them used inconsistently with how they're used now. However, that situation has changed, and so there's people are in the process of switching their terminology over so that reproducible means that another team can obtain the same result using the same experimental environment, and replicable is a little bit stricter, where another team can obtain consistent results using a different experimental environment. And I'll point you to these links in the chat. You'll notice that there is there's a link to our kind of online material associated with this tutorial. And that online material has a page with all these links in it, because I know the links don't come through Zoom. So if you want to use the link instead of having to type very quickly, you can browse our online material and get to the links there. Okay, so now we'll have I'll start off with why reproducibility is important. And I know I'm preaching to the choir a little bit here, but you can take these and you can share them with everybody and tell them, they all need to work on reproducibility because it's important. there's, and I think it's pretty well known now, there was a study a couple of years back from the cognitive science literature where researchers took 100 articles that had been published in their field, and they tried to reproduce the results of those 100 studies. And it turned out they could only actually reproduce 40 of them. And that was kind of an eye opener for having 60 results now, which have this status of having to be redone or reworked because they can't be used as the basis for future experiments. If you're not able to reproduce the results, how can you be sure that you can build on that result? We might think that we've escaped this in the physical science or in computation, and we haven't necessarily similar. We have problems whenever we have issues trusting the software that's producing our science. So one of the key takeaways here is that the scientific results from computation are only as good as the software that produced them. And here's an example of something that happened a couple of years back. In 2009, there was a study from a group at Princeton showing that there were 2 different phases of liquid water between -40, where it just definitely freezes to ice, and 0, where it should freeze to ice eventually. And so the supercooled region of water in their simulation model had 2 different liquid phases with 2 different densities. And later on, a couple of years later, there was another group that did a simulation of supercooled water and found out that there was only 1 phase, a high density phase. The 2 results, of course, disagreed, and they had to figure out exactly what the disagreement was and whether it was 2 or 1 phase. And so the De Benedetti group looked at the Chandler paper, which says, okay, the LAMMPS code, the second paper says the LAMMPS code is a standard and documented, and our scripts for running it are freely available upon request. So of course, De Benedetti group asked for the code with his colleague Palmer, and it wasn't necessarily forthcoming until some appeals to the editor of Nature, when Palmer finally got this code and looked through it and reproduced the second result. He realized that there was actually a feature that the Berkeley group used in the LAMMPS execution to speed up the execution of the algorithm. But that feature, which sped up the running time of the code, ended up that feature ended up actually changing the physics of the result. And what was even worse, and the resolution took 7 years, and what was even worse is that there's no way you could have actually known whether the result was correct or not, because you couldn't reproduce it just by reading the paper. So it is actually really important to publish these appendices in your papers that explain, how do you exactly go about reproducing your scientific results. And unless we think this is related to HPC numerical codes in C++, there is also a story of an NMR library that's used to interpret data from NMR experiments that uses a standard library from Python called glob. And glob just returns a list of files, but because it returns the file list in a different order, depending on what operating system you're running on, you can actually get different results from the NMR analysis code based on which operating system, like Linux versus Mac. And so that casts some doubt on the scientific results of about 150 papers. Something that's concerning about this is that it's not necessarily the case that a good unit test would have caught it, because not every unit test is comparing results between architectures. And so this is kind of a really sticky issue of how do we know when something is 100% bug-free and tested and working. And in many cases, this comes down to working with code to show that your software is doing what you say it's supposed to be doing. So that your science can be as good as it possibly can be. You want to make your software as good as it possibly can be. All right, so now that I've talked about why you want to increase reproducibility, I'm also going to talk a little bit about the community and the incentives for paying attention to reproducibility. This is something that we could probably have a good discussion on in this conference. So, are we doing enough to encourage it, and how do we work with the fact that how do we live with the fact that we're on teams that have real deadlines and real goals, and we have to get papers out, and we have to publish. There are academic institutions that have 10-year timelines that push you to get everything that you possibly can do in as short a time as you can. But the reproducibility is also important. So we have to think about the incentive structures that exist in society, and how do we change those incentives to make sure that they're rewarding people for actually producing better, more reproducible science. We mentioned before, supercomputer cycles are scarce resources, but not just that, we want to have confidence in our results, and we want our readers to have confidence in our results. So we have to think about ways to increase the credibility without actually requiring that we repeat things. Sometimes if you're on special hardware with a quantum computer that's only available to 1 or 2 people in the world, you can't even reproduce that because the computer's moved on to its next problem. There are a couple of agencies that have provided some guidelines, like the Fair Data Principles, that allow us to talk about what we're doing and why we're doing it for increasing the credibility of our source code. There are also NSF policies on dissemination and sharing of results, and the requirements of data management plans that are also good steps in this area. There are several publishers that have taken up the cause, and here's an example from the SC Supercomputing Conference, where there are appendices that you can put in your paper. Artifact description says how you ran it, and this is mandatory. Artifact evaluation is a little bit more detailed and talks about the trustworthiness of your result, especially for things where rerunning is hard or impossible. There are some big publishers that are also involved in these sorts of efforts. One in particular is the ACS TOMS reproducible computational results. And with this process, it's actually a really good example, I think, of a process to encourage reproducing results, because when you submit a paper for evaluation with RCR and you get this badge at the end of the process, you end up getting a reviewer who is not anonymous, but who works with you in order to go through your entire process and reproduce your results. And at the end of that, they actually get to publish a companion like mini paper that talks about the process of reproducing the results, which means that the person who spent the time and effort to do the reproducing gets credit for their work. The journal gets to show that it has a quality, rigorous paper, and the reviewers and the authors, of course, get their badge indicating that it has additional credibility. So it requires effort, but you also get to see that effort. And so these are kind of strategies that they create this virtuous cycle that we've already mentioned before. Since we've compressed our talks and timelines a lot, I don't have a huge amount of time to go through all of these strategies to improve reproducibility. However, I can summarize them all by saying that the good software development practices that we know and love are also great ways, are also the same ways that you can use to improve reproducibility of your code, or improve of your scientific code and software. And so this is broken up into strategies during development, strategies after development, and strategies during runtime. During development, probably the very first most important thing is actually solid versioning practices. If you're using Git and version control, then you already have commit hashes, but above and beyond that, Git lets you create tags. You can use those tags and make up tags every time you do a new run. And it's actually not a bad idea to do that, because then you are always able to trace back the lineage of your runs. It works even better if when you do a run and you produce an output file, the output file can say what tagged version or what commit version of the source code was used when that was run. Of course, that means you also have to keep your, you have to make a commit to your code before you run it, and that's not often done. And you also have to, it's also a great practice if you keep your tests and your documentation in sync with your code, so that you can move everything forward as one package that's running. You also want to try and follow good coding standards and build in quality to your code from the start. And this is not just coding style, but also kind of what is the expectation for people who are adding to your project, what kind of documentation, what kind of tests, and of course, as your code gets results that are more and more important, you should spend more and more effort on the testing process and showing that your code is doing what it's supposed to be doing. Another great way to get quality into your code is by practicing peer review. During development, there are some numerical issues that you should watch out with floating point precision or integer rounding. Probably we're aware of these, and we can think of great ways to look at and analyze them. Testing, we've talked a lot about testing, so there were some talks on that already. Something that is important to keep in mind is that you're not necessarily just having to test your code. You might want to make sure that you have some tests that cover the state of your system, because if you're working on a computing system, sometimes the libraries and the modules and the kernel versions of that compute system that you're working on are updating. So you want to test that everything is still as you expect, kind of the base level system. We can digress on physics-based tests. I'm not going to dwell on this too much, but there are physical ways there's information in the physics of your problem sometimes that can help you to devise test. And there's also a way to think about tests where you check that your inputs and your outputs are conforming to your expectations. And those are nice tests to have, because like assertions in your code, a lot of people work with those and understand them pretty well. Now, during experiments, this is also some important stuff to keep in mind. And I want to summarize all of the information on improving reproducibility during experiments as saying that this is like having a great data management plan. It might not sound like the most fun thing to do, but in fact, we had, I think on day one of this conference, a great talk about just the workflow that takes source data from outside inputs and moves it through transformation phases and outputs it to final data products, capturing the steps in that workflow, either by writing it down on your notebook, like an actual pen and paper laboratory notebook, or keeping it in scripts and version controlling those scripts is a great way to show how your data is flowing. You also, as you're building up your science, if you're scaling to larger system sizes, you want to try and have an idea of how big your inputs and outputs are and what data products you want to keep. If you know that your final code is going to produce a terabyte of output data, maybe you want to try and save some intermediate checkpoints along there to use as part of your validation process. All right, so be thorough and capture. All those things are kind of provenances. They're related to provenance, which is just showing the chain of events that led to the output that you have. So if you can show, what steps ran to it, what versions of external utilities and tools and libraries all went into those steps, all that is great to show all the information that went into your outputs. Okay, and capturing and documenting all of this, obviously, even after your experiment's done, you want to have a long-term storage plan. There are some tools. This is a small tool list, and probably from the things that I've heard at this conference, we should add some more tools to this list. And just to summarize, the credibility of your science derives from the credibility of your code and your process. And because we want more credibility and we want better science and more reproducible science, stakeholders are ratcheting up expectations for reproducibility. We also have great design strategies that I've talked about a little bit for improving reproducibility and testing in all the phases of your science process. And these are just really closely linked to better development practices. All right, so I'm moving through these kind of quickly, and now I'm going to summarize for the day, and we'll have time to ask questions and do an interactive session afterwards. Looks like I did get a bunch of questions for this, though, so maybe I should take some time to do that.
There's a question from William in the chat. Are you using automated scanning tools for peer code reviews? And if so, what are your recommendations?
I don't have any experience using automated scanning tools. Actually, I want to take that back. I have looked at sorcery.io, which is it's a tool that scans through your Python and tells you what your readability for your code is. And it's nice. I mean, it gives you some inputs on your code. But I think for now, there's not really a substitute for actually having a human that you can talk to, because sometimes the problem is not necessarily your code. It's more, you know, are you putting the updates into the right place, and are you structuring your work the right way? All right, so that we don't get over time. Oh, and there's other resources, and these are also on the webpage. And also feel free to go back and look at these slides as they exist in the webpage and use them for checklists and creating your own process. To summarize, I will kind of try and cover what we talked about today as a BSSW tutorial as best as I can. Scientific software is increasingly being held at the higher levels of scrutiny, and there's some big stories about this. You may be familiar with the story of the Neil Ferguson's epidemiologically modeling of the COVID-19 pandemic that predicted that there would be a very large spike in infections initially in 2020, and that led to government action in UK Parliament. But not everybody was happy with the way the code was structured. There was a person, Nicholas Lewis, independent climate science researcher, who looked at the code and said, well, I can't easily see where your assumptions come from. And by looking at your code, it's not at all clear. And so he called it, kind of unverified and undocumented inadequately, if at all, although he's from a different field. So again, science versus coding style kind of clashes a little bit here. But the news picked up on this because it was a big news article. It was a hot topic, and they brought in some outside experts from industry who said, well, we would hire anyone who developed code like this because they're from different fields. Because the industry is, has different coding standards than academics, and the models must be capable of passing basic scientific tests of validity. So professors from all kinds of different fields commented on this, and then there were some bugs that were found in the code, which had to do with the reproducibility of running in a specific parallel configuration with a specific output file. And although the scientific part of the scientific process is finding and responding to inadequacies and small changes and issues with the code, we really need to be able to understand whether or not our source code is doing what we expect it to do, and how do we go through the process of making it work. What you may not have heard is actually there are other people on the other side who are saying, well, the quality of academic code is not necessarily the same as the quality of industrial code. And then industrial people who are not, so people who are experts in industrial software design practices don't necessarily know what the science is that's behind it, or how the scientists are verifying their code. And so, we're talking across purposes a little bit, and we can't necessarily jump to conclusions. And CodeCheck is an organization that does some independent reproducing of computational results. So they took up this problem, and they found that they could actually reproduce Imperial Report 9 with newer versions of the code that went through and fixed some bugs. And so it's one of these issues that's conflating the outcomes of our science with the inputs of our scientific code. And as scientific code, and the lessons that we can take away from this are that as scientific code becomes much more important in producing the things that we work with every day, and producing results that are important for society to move forward, your code might be used in ways that you don't expect and by people you don't know. And these consequential decisions really ought to have a scientific code that is as well checked and vetted and as thoroughly reviewed as possible. A question, though, is, even though in this case it seems that the code and results could be verified, is it okay to actually excuse scientific software for being crappy stylistically? And as a hint, good software development practices are giving us better assurances that our scientific codes are working. So it's actually It's better if you can to make your code as clean and modular as possible, because we want our science to be as good as it possibly can. We covered a whole lot of topics today: project management, collaboration, software flexibility, testing strategies, how to refactor, how to think about and talk about the reproducibility that we want from our science codes. There were a lot of things that we didn't have time for. Luckily, some of the other talks kind of jumped in and gave us some ideas for this. There's only so much time in the day, but it's important to look at all of these and think about how we can adapt these strategies to make our science better. Some people might come back and say, we're a researcher, we can't afford to spend all of our time on software engineering. And for that, I say, yesterday there was an awesome PSIP tutorial that talked about how you can build a plan for improving the process on your team. So I'm just going to throw this slide up here and remind you that there was a great tutorial on this yesterday. And if you want more info, you can look at some of the resources we have. Thanks everyone for your inputs and for interacting with us during the BSSW tutorial. We are going to open up time now so that we can have discussions and talk about all these things in more depth. And I'm giving you here a slide with ways to keep in touch with the team. So thanks. David, how do you want to structure the next steps and breakouts?
There is a question in chat.
Oh, okay.
Or a statement.
Let's do that. Did I miss anything, or is this the next one?
I can read it out loud if you'd like. It's just, this question part is the second half, but essentially it's like you already covered many similar and great arguments about better scientific software and why we should pursue that. I'm thinking specifically about incentive structures, but what do you see as necessary towards shifting incentive structures at most research institutions and within science culture itself towards truly prioritizing better scientific software practices you were describing?
Okay, so yeah, the $1 million question. And if I had an answer for that, then I would share it with the world. I've talked about the things that people are doing, and I've talked about ways that we can communicate those in our kind of circles. I think that's the right place to start, to just, to think about the fact that funding agencies and publishers view this as, and researchers view this as an important problem. And whenever you're up against, people who don't view it as an important problem, then kind of cite some of these examples. But also taking part in some of the organizations that are moving this cause forward are another good way to get involved.
Yeah, thank you. I just remember like a talk a while back, separate from this, highlighting just well-documented, reproducible code gets greater citation rates and recognition. And I think that's just one of the preeminent ways that's been effective for me in convincing others, but it's still sometimes a uphill battle with some groups.
Yeah, it definitely can be. This is a real culture change that we're talking about here, and it's going to take time and it's going to take effort. There are things that can happen, from the ground up. We also can use some help from program managers and sponsors and managers to help put emphasis on these things. And so in the Ideas Project, we're pursuing a variety of tactics. We are in communication with program managers about some of these ideas and things to proceed with there. And just by way of example, there are some funding opportunity announcements that have come out from parts of DOE that ask not only for a data management plan, but for a software management plan or a software sustainability plan. And so that's just one way of ratcheting up the attention that's paid to these kind of things. All right, so we finished the presentation portion of the tutorial. We have a few minutes before the break, and then we have another hour after the break. And so let me just share my screen for a moment and talk about how I thought we would organize things. So this is the website for this particular tutorial, and I wanted to highlight the hands-on activities here. So we have a set of hands-on activities not associated with every module, but associated with a number of them. These are things that you can work through. You can do it at any time. So there's a module to work through how to use GitHub to set up a Kanban board, and so you can sort of practice how that approach can work with the particular tool. If you're less familiar with Git, you might want to look at the Git for collaboration. Well, you'll fork a repository and create a branch and make a pull request. These are the basics of collaborating with Git. We have some stuff on software testing and also refactoring. These are using the heat equation codes that we've talked about in many of our presentations. So it's fairly simple. You don't need to understand the math to do it. I think we have pretty good instructions here. There are a couple of things that we didn't have time to present today, but are also there, and we do have presentations if you want to learn more, a little bit more about Agile and Epic Story Task and some of those types of things, and then also continuous integration. So that's one possibility for things that you could do. And we will have breakout rooms where people can work on that. Well, if you want somebody to kind of walk you through one of the hands-on activities, we can do that. We'll have one room set up for that. We'll have another room where you can just work quietly. You can pop back up and ask questions, or we'll check in on you occasionally. We also have opportunities to do more Q&A about the presentations, or we can talk just more generally about scientific software and scientific software processes, process improvement, and things like that. So it's really meant to be open-ended. It's meant to be driven by you as participants. What would you like to do? And so we have a few minutes right now where if we can make the breakout rooms available, maybe people can get started. We will, let people go to the break, but then we'll have opportunities afterwards to continue discussions or work on the hands-on activities or whatever you would like. How does that sound to folks? And feel free at this point to unmute, maybe raise your hand if you want to say something or ask a question. I think we can be pretty informal here.
Hey, this is Ed Hartnett. And first of all, I want to say great presentations. And I can't count the number of times that I have been saying to myself, I wish I had this material years ago when I tried to make kind of presentations to explain stuff to people. So this is a really great resource, and thank you very much.
Thanks, Ed.
One thing that I do hear coming up a lot that concerns me, or kind of has been a pain point in the past, is that when you tell people to program for the future or with the future in mind, a lot of times they think what that means is they should write a bunch of code for things that are not needed now, but might be needed someday. And that's a pretty bad idea. And so it should also be emphasized that the code that solves requirements in the least number of lines and entities is the best. And to double your code size and keep your requirements the same means you're doubling your cost, or more than doubling your costs, without any benefit to the user. So smaller is better.
Yeah, that's a really good point. This is a fairly general principle in software engineering that I've heard called YAGNI. You ain't gonna need it. YAGNI. And it's basically saying, don't put things into the code because you think you're going to need them later. Just make it possible so that later, if you really need them, you can, add them, you can extend to incorporate them in a straightforward way. So don't do more work than you need until you need to.
Yeah, just to second that, there was the one line on one of the slides that made the point that the future will have unexpected things in it. Plan for them.
Yeah.
That's sort of asking people to plan for the unknown is sort of hard. But yeah, but I think there's a more subtle meaning.
Yeah, part of the planning for the unknown, I think, is trying to think in the bigger picture, think about good sustainable and extensible designs and things like that. Try to find the right abstractions to deal with and those kind of things. Those tend to sustain over time.
If I could chime in there briefly, I think that made me think of just like a current kind of issue I'm kind of contending with in terms of some of our like GPU kind of porting projects. And there's a lot of discussions there in terms of like, whether we should using, this approach like OpenACC, OpenMP, there's Coco Swaja, there's all these different languages approaches that allow or sometimes prevent portability in various ways. And people want to try to like plan out ahead and future into that space. But I think the better maybe argument to make, as you're highlighting here, is to just design for the abstraction level. So like if you do need, focus on what the system you're targeting today, and hopefully the design elements of the algorithms you are in fact parallelizing for the GPU are in fact able to be easily ported to a different system with minimal code changes, and it's actually in fact maintainable across a longer life cycle without necessarily needing to constantly being on your toes about what technology might be the one end up being chosen for the future. I'm just making a statement there, but I think I just like that idea in terms of just like focusing on the kind of like the abstraction level and not trying to predict the future and which will work the best.
I agree wholeheartedly, and also would say that the code that's easiest to adapt to a new system is code that is very well tested and documented, and now it is easier for me to make changes to it. So the process of adding testing and good documentation to your code definitely supports the porting of that code to a different platform. I'm sure we all agree.
And probably we should qualify that for me, I tend to be cautious about the future. So plan for the future means defensive coding styles.
Do you want to expand on defensive?
Well, yeah. So when you're coding defensively, you're thinking, how could people accidentally misuse this code, and can I figure out, a quick check on my inputs or a test that I can add in my test suite to make sure, or a design structure for my data so that you can't pass me data that's going to make the code look invalid.
So that's part of what he was saying on the testing too. Yeah. And so what I hear is modularity, testing, and documentation, and defensive programming, I guess, development, which is partially the testing too.
What other experiences are people having with their software development? What kind of challenges are you facing?
Well, I'm going to pipe up here. I think the change in teams has been really affecting us a lot. So some of these processes are really important in that area.
The change in what?
Team membership on a project.
Oh, the turnover
Right.
of people on your team, of onboarding and then offboarding.
Yeah.
Okay. You did talk about that at one point, the
Yeah.
onboarding and offboarding.
Yeah. Just out of curiosity, how many people here are working with people who they've never met face to face because of COVID? So people who are new to their teams, and in the last couple of years. Just raise your hand in Zoom. Yeah, there's a good few. Is that a challenge to people? Is it different being slowly remote rather than having face-to-face contact?
I have been fully remote since long before COVID, and also when working on the NetCDF project, was working for decades with many people that I still work with and yet have never met, or have only met, at a conference, and they come up and say, hey, and we shake hands, and that's pretty much it. And I think that the GitHub tools really support remote collaboration well if you use them properly.
Mm-hmm. Yeah, Eric commented that COVID has kind of been an equalizer in making everybody remote instead of just, one or two people. And I can agree with that too. Oh, I noticed the time. So technically this is break. So feel free to take a break. I'm happy to stick around. We can continue the conversation. And of course, we'll be back after the break.
And you might lower your hand so we don't think you're asking a question.
Oh, yeah.
And we're going to use the breakout rooms after the break so that we can have more individual discussions. So we'll think about them as kind of an extension of networking, or just walk through some of the hands-on and do, talk shop.
Yeah, so we'll be back in a few minutes.
Oh, so I thought I was going to be late, but it looks like the breakouts haven't started yet.
Yeah, we are on a break, Anshu. We just went on a break.
Yeah, I know.
A little bit organized. I'd like to get a little bit organized about what we're going to do with the remaining time. So we have several options. As I mentioned, I just put in the chat again, a list of hands-on exercises. So if anybody's interested in those, maybe you can raise your hand in the Zoom reactions. You're also welcome to do those on your own. All right, I'm not seeing any. We can do those at any time. And then another option would be to have some more Q&A that's specifically related to the presentations. If there was anything maybe that we went over too quickly because we're a little bit rushed, a couple points or things like that, we have a room that we can spend some time going deeper into some of those things. Does anybody care to do that? Please raise your hand. All right, so, oh, Eric. Great. What did you have questions about, Eric? So we can send the right person in with you.
Oh, actually, I thought that last breakout room is the one I wanted to go into, and I think I'm going to have to go through some of the talks and decide what I need to ask specifically. I'm not sure right now, but I think that just sounded like the most interesting one to go to.
Okay.
So,
so you can feel free to go ahead and go in there, and if you want to spend some time sort of flipping through and thinking about your questions,
yeah. Okay.
And maybe I'll come in a little while, or somebody else will come in, and we can talk more about whatever you have in mind, and other people can go join too. And then we have a couple of rooms if people just want to have sidebar discussions. It could be with us as presenters or amongst yourselves. And then I thought in the main room we would just sort of continue chatting about your software experiences and sort of talk about challenges that you might be facing that
Okay.
you might want to discuss as a group or things like that.
Okay.
Anything you're willing to share.
Do you have the slides available, by the way, for the presentations?
We do.
Okay.
They're all on that website that I keep referring to, and I
Yeah,
can,
right.
and I keep wanting to use that, but I can also give you the exact DOI.
Okay, whatever URL you want to release that we can go to. Okay.
It's all there. Just
Okay.
The tutorial website's the easy place to always go to. Couple clicks, you can get anywhere else.
Right. Okay. Cool.
Yeah, even there under the resources, you can click to any of those, the things that, the sites that we have in the slides.
Yep. All right. So, well, if nobody else wants to kick off the discussion, I was going to ask, we talked about a whole range of techniques. I'm a little bit curious what people might have found, maybe something that they might not be doing currently in their projects that they really want to take back and try. Sort of what's the first interesting thing maybe you discovered in what we talked about? Is there anything that was new to you here?
Well, this came up earlier, the PSIP, which you also talked about in the, what was the term, process?
Productivity and sustainability improvement planning.
Well, and there was these cards, I forget the name of it.
Okay.
Task, project task.
PSIP cards.
Project tracking cards.
Yeah,
Project tracking cards. Yeah, and we talked about that before, and you talked about it as well. And so that was kind of a new idea for me. And we went through an exercise before with the PSIP talk, which I think is, I don't know the relationship between that and you.
So it's the same larger project. We're both in the
Right,
ideas
okay.
project. David is among David Rogers.